What if the universe operates on hidden patterns we're only beginning to understand? Picture this: every spiral galaxy, every swirling nebula, every orbit of a distant planet, they all follow rules we can't fully see, like a grand cosmic dance choreographed by invisible hands. For centuries, scientists and philosophers have gazed up at the night sky and wondered whether there's a deeper order to everything, a kind of hidden symmetry that holds the cosmos together. And what they've discovered might just reshape everything we thought we knew about reality itself. This isn't just about beautiful shapes or pleasing patterns. We're talking about the universe's hidden symmetry, the subtle, often invisible principles that govern everything from the tiniest particles to the largest structures in space. Think about how a snowflake's intricate design repeats itself no matter how you turn it, or how the branches of a tree mirror each other in perfect balance. Now imagine that same idea applied to the laws of physics, to the birth of stars, and even to the nature of time. It's these symmetries that may hold the key to unlocking the universe's greatest mysteries. In this video, we're going to explore 30 incredible theories about this hidden cosmic order. Some will challenge your understanding of space and time. Others might make you see the world in a whole new way. We'll journey through ideas that connect the very small to the very large, revealing how symmetry isn't just a mathematical curiosity. It could be the foundation of reality itself. So settle in and open your mind, because what comes next might just change how you see the universe forever. Let's begin with one of the most elegant and profound ideas in all of theoretical physics: supersymmetry, often called SUSY. At its heart, this theory proposes a breathtakingly beautiful and hidden symmetry in the laws of nature, one that connects the two fundamental classes of particles that make up our universe. On one side, you have the fermions. These are the building blocks of matter, like electrons and quarks. On the other, you have the bosons, the force carriers, like photons that carry light, and gluons that hold atomic nuclei together. For decades, these two families were treated as completely separate, governed by different rules. But supersymmetry suggests they are actually two sides of the same cosmic coin. The theory makes a stunning prediction. For every known particle in the standard model of physics, there should exist a hidden, super-heavy twin, a superpartner. An electron would have a partner called a selectron. A quark would be paired with a squark. Even the photon, the particle of light, would have a shadowy counterpart dubbed the photino. This isn't just a whimsical idea, it solves some of the most glaring problems in modern cosmology. For instance, the mathematics behind the Higgs boson suggests its mass should be astronomically larger than what we observe, almost to the point of breaking our models. But these proposed superpartners would naturally cancel out these extreme values, acting as a kind of cosmic counterbalance that keeps the universe stable and mathematically consistent. Perhaps its most compelling promise is a solution to the mystery of dark matter. Our observations of galaxies show they are rotating so fast that they should fly apart, yet something invisible, a huge amount of mass we can't see, is holding them together. None of the known particles account for this, but the lightest of these proposed superpartners, often thought to be the neutralino, would be stable, electrically neutral, and barely interact with ordinary matter. It would simply permeate the entire cosmos, forming vast, invisible halos around galaxies, a perfect candidate for the elusive dark matter that makes up over 85% of the universe's material. So why haven't we found it? Experiments at the Large Hadron Collider, the most powerful particle smasher ever built, have been hunting for signs of these superpartners for years. They've created billions of miniature collisions, recreating conditions a fraction of a second after the Big Bang, searching for the unique energy signatures that will be left behind if a superpartner were created. The fact that they haven't found direct evidence yet doesn't mean SUSY is wrong. It might simply mean these particles are far heavier than we initially hoped, placing them just beyond our current energy reach. The mathematics of supersymmetry remains so powerful and so elegant that many physicists believe we are on the right path, and that the next generation of experiments might finally reveal this hidden layer of reality, confirming a symmetry so profound it would redefine our place in the cosmos. But if supersymmetry hints at a hidden kinship between particles, then our next theory takes us even deeper into the fabric of reality, proposing that these particles aren't even the most fundamental things in existence. Imagine if every single particle, every electron, and every quark wasn't a tiny dot, but instead an unbelievably small, vibrating loop of energy, a string. This is the bold premise of string theory, which suggests that what we perceive as different particles are actually just different notes on a microscopic cosmic instrument. The vibration of the string, how fast it oscillates, and in what mode determines whether it manifests as an electron, a photon, or any other particle. In this symphony of strings, the entire universe is composed of nothing but these tiny, vibrating threads of energy. Now, for this elegant idea to work mathematically, these strings can't just vibrate in the three spatial dimensions we experience. The equations of string theory only make sense in a universe with 10 dimensions. This immediately raises a colossal question. If there are 10 dimensions, where are the other 6? The theory's answer is both brilliant and mind-bending. It proposes that these extra dimensions are curled up into an infinitesimally small, intricate shape at every single point in space, far too tiny for us to ever perceive directly. Think of it like a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant, you'd discover that the hose has a second dimension, a circular cross-section, curled tightly around its long axis. In the same way, our reality might have 6 dimensions tightly wound up at the quantum scale. The specific geometric form these hidden dimensions take is absolutely critical. Not just any shape will do. It must be a very special type of complex, 6-dimensional shape known as a Calabi-Yau manifold. The properties of this miniature geometric knot are what ultimately dictate the laws of physics in our macroscopic world. The shape of the Calabi-Yau manifold determines how strings can vibrate within it. Each allowed vibration mode corresponds to a different type of particle with specific properties, like its mass and charge. In essence, the manifold acts like a cosmic musical instrument, and its geometry is the instrument's design. A differently shaped Calabi-Yau would produce a completely different set of vibrational notes, a completely different set of particles and forces. In a very real mathematical sense, the entire universe we see around us, the fact that there are electrons, that light behaves as it does, that gravity is weak, is a direct consequence of the specific geometric form of these hidden, multidimensional spaces. Visualizing a 6-dimensional object is, of course, impossible for our 3-dimensional brains. But mathematicians and artists have created stunning projections of Calabi-Yau manifolds, allowing us a glimpse of their breathtaking beauty. They often look like impossibly intricate, multi-hole jewels or fantastical organic forms with tunnels and bridges, a labyrinth of extraordinary complexity folded in on itself. The profound hidden symmetry of our universe may be encoded in the elegant geometry of these shapes. The fact that our universe allows for life and complex structures might not be a random accident, but a direct result of the specific Calabi-Yau manifold that our cosmic strings chose to vibrate within. It's a theory that suggests the deepest laws of nature are not just written in a language of mathematics, but in the language of geometry itself. Yet if the geometry of hidden dimensions redefines what reality is made of, the holographic principle challenges our most basic intuition about where reality actually exists. This theory proposes something that sounds like pure science fiction. Our seemingly rich 3-dimensional universe, with its galaxies, planets, and everything we see and feel, might not be the fundamental reality. Instead, it could be a magnificent projection, a cosmic hologram emanating from a distant, two-dimensional surface that contains all the information needed to describe our world. To grasp this, think of an ordinary holographic sticker. When you tilt it, you see a three-dimensional image, a bird that seems to fly or a planet that appears to rotate. Yet all that information, the entire SEEMINGLY Chinese letter image, is encoded on a flat, two-dimensional piece of plastic. The holographic principle suggests our universe operates on a similar, though infinitely more complex, scale. The three-dimensional volume of space we inhabit, along with everything within it, could be a projection from a two-dimensional surface at the very boundary of the observable universe. The origins of this mind-bending idea come from a deep puzzle in theoretical physics, the black hole information paradox. When something falls into a black hole, it seems to be lost forever, violating a fundamental law of quantum mechanics which states that information can never be truly destroyed. Physicist Leonard Susskind found a fascinating way out. He calculated that all the information about every object that has ever fallen into a black hole is not lost inside its mysterious interior, but is instead perfectly encoded and preserved on the black hole's event horizon, its two-dimensional point of no return. The event horizon acts like that holographic sticker with a perfect 2D record of everything that fell into the 3D void. This realization led to a far more radical and universal application. Perhaps this isn't just a clever trick for black holes, perhaps it's a fundamental property of the entire cosmos. In this view, the universe itself has a boundary, a distant 2D surface, and every event, every particle, and every force we experience here in the 3D bulk is just a reflection of information being processed on that remote cosmic screen. The laws of physics in our world would then be a direct consequence of the physics playing out on that lower dimensional boundary. This creates a profound and hidden symmetry between the surface and the volume. It suggests a universe where the maximum amount of information any region of space can contain is not proportional to its volume, as we would naturally assume, but to the area of its surface. Imagine a sphere. You'd think the amount of data needed to describe its interior would grow with the cube of its radius, its volume. But the holographic principle says it only grows with the square of its radius, its surface area. Our perception of a rich 3D world is in a way an illusion, a very detailed and consistent one, but an illusion nonetheless. The true, fundamental workings of the universe might be happening on a flat, distant surface we can never see, making our reality the most grand and complex hologram imaginable. While the holographic principle reimagines the very dimensions of reality, another profound symmetry operates within the space we know, governing how matter changes its very state. This brings us to a cornerstone of theoretical physics known as conformal field theory. At its heart, this is the study of systems that possess a very special and powerful kind of symmetry. Imagine taking a complex, intricate map like the coastline of a continent and being able to zoom in or zoom out on it. As you change the scale, the large bays and inlets you saw from space begin to reveal smaller peninsulas and coves, and then even smaller rocks and grains of sand. Yet, no matter how far you zoom in or out, the pattern of the coastline looks essentially the same. The angles between all the features remain perfectly preserved, only the distances have been rescaled. This preservation of angles, but not necessarily distances, is the essence of a conformal transformation, and it reveals a hidden self-similarity woven into the fabric of nature itself. Conformal field theories are a special class of quantum field theories that remain completely unchanged or invariant under these kinds of scaling transformations. They are the mathematical language we use to describe systems at a critical point, the precise moment of a phase transition. Think of water turning to ice. For most of the process, the system is either mostly liquid or mostly solid. But at the exact temperature of 0 degrees Celsius, the system becomes critical. It's caught between two states and fascinating phenomena emerge. At this critical point, the properties of the system become scale invariant. If you could look at the arrangement of water molecules at the instant they are forming the crystalline structure of ice, you would see clusters of molecules aligning. And the remarkable thing is, these clusters look the same whether you examine a region a millimeter across or a nanometer across. The pattern repeats itself at every scale. A classic and beautifully simple example of this is the Ising model. Picture a vast grid of tiny magnets like atomic-sized compass needles. Each magnet can point either up or down. At high temperatures, the magnets are all jumbled, pointing in random directions due to thermal energy. This is a disordered state. At very low temperatures, they all align, pointing in the same direction to create a large, organized magnetic field. This is an ordered state. But at one specific, critical temperature, the system goes wild. You see massive, swirling fractal patterns of aligned magnets with clusters within clusters within clusters. A snapshot of this critical state would look identical whether you scaled it up or down. The physics governing these magnets is described by a conformal field theory, which captures this perfect self-similarity and allows physicists to calculate exactly how these patterns behave. This symmetry isn't just a laboratory curiosity, it's etched into the natural world all around us. The branching of a tree, the forking of a lightning bolt, the flow of a river delta, and the complex structure of a cloud all exhibit this same scaling symmetry. They are visual echoes of the same critical phenomena that conformal field theories so elegantly describe. The power of this framework is that it provides a set of universal mathematical tools that work regardless of the microscopic details. It doesn't matter if you're studying magnets, fluids, or subatomic particles. If a system is at a critical point, its behavior is governed by these universal conformal principles. This means the same equations can describe the freezing of water and the alignment of spins in a magnet, revealing a breathtaking unity underlying seemingly disconnected events in nature. It's a hidden symmetry that doesn't just describe objects, but describes the very process of transformation itself. Yet the most concrete and powerful application of the holographic idea isn't just a general principle, it's a specific, mathematically precise blueprint known as the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT for short. This is not merely a suggestion that the universe could be a hologram. It is a full-blown duality, a profound equivalence between two seemingly utterly different descriptions of reality that are, according to the math, one and the same. To grasp this, we first need to picture the two sides of this incredible duality. On one side, we have a special kind of universe, an anti-de Sitter space. Imagine a cosmos that is not flat and not expanding like our own, but is instead shaped like a giant hyperdimensional bowl. In this curved, warped space-time, gravity operates as described by Einstein's general relativity, and it contains strings and black holes, a full gravitational universe in a box. Now, the key feature of this bowl-shaped universe is its boundary. Because of its unique curvature, this boundary is actually a flat, lower-dimensional surface that sits at an infinite distance from any point inside, yet it remains perfectly finite and accessible in the mathematics. On the other side of the correspondence, living precisely on that flat boundary, is a conformal field theory. This is a quantum field theory, like the ones used to describe the strong nuclear force that glues atomic nuclei together, but with that special scale invariance we just discussed. It is a theory without gravity, where particles interact on a rigid, flat stage according to the rules of quantum mechanics. The astounding claim of AD-S/CFT is that these two worlds, the gravitational universe in the bowl and the quantum theory on its boundary, are completely equivalent. They are two different languages describing the exact same physics. Every single process that happens inside the gravitational bulk, a black hole evaporating, two strings colliding, is perfectly mirrored by a corresponding process in the quantum field theory on the flat boundary. A complex calculation involving warped spacetime and gravity in the interior is exactly mirrored by a different but equally valid calculation involving particles and quantum forces on the edge. The boundary theory doesn't just describe the interior, it is the interior written in a radically different code. This duality provides physicists with a spectacularly powerful tool, a kind of computational wormhole. Some problems are fiendishly difficult to solve in the gravitational description. For instance, understanding what happens inside a black hole, at the very center where gravity becomes infinitely strong, has always been a nightmare for physicists. But through AD/CFT, they can translate that impossibly hard gravitational problem into a different problem in the well-understood language of quantum field theory on the boundary. They can solve the quantum equations there and then translate the answer back to understand what's happening deep inside the black hole. It's like trying to understand a complex sculpture by feeling its shadow. By studying the shadow with perfect precision, you can learn everything there is to know about the sculpture itself. Conversely, the correspondence works the other way, illuminating the mysterious behavior of certain quantum forces. The strong nuclear force which binds quarks together to form protons and neutrons becomes incredibly intense when you try to pull quarks apart. It's like trying to separate the ends of a rubber band. The harder you pull, the stronger the resistance. This makes it extremely difficult to study using standard mathematical techniques. But through the looking glass of AD/CFT, this very strong nuclear force in our flat world can be mapped onto a much simpler gravitational theory in a higher dimensional curved space. Physicists can use the easier math of gravity and black holes in the bulk universe to calculate properties of the fiendishly complex strong force in our own, providing insights into the fundamental glue that holds all visible matter together. This holographic bridge, connecting the deepest puzzles of gravity to the most complex problems of quantum physics, stands as one of the most promising avenues for finally forging a complete theory of quantum gravity. While the holographic principle and AD/CFT duality stretch our imagination across dimensions, there exists a symmetry so fundamental and ironclad that physicists believe no matter what new laws we might discover, it must always hold true. This is CPT symmetry, the ultimate cosmic rule that the combined operations of charge, parity, and time reversal must leave the laws of physics completely unchanged. To understand this profound idea, we need to break down its three components. First, there's charge conjugation, or C. This is the idea of swapping every particle with its antimatter counterpart. Imagine a universe where every electron is replaced with a positron, every proton with an antiproton. It's like creating a perfect anti-world made of mirror matter. Next is parity, or P. This is a spatial mirroring, flipping the universe as if reflected in a giant mirror. In this looking glass world, everything that was right-handed becomes left-handed. A clock's hands would appear to rotate backwards, and your heart would beat on the right side of your chest. For a long time, physicists assumed this symmetry was perfect, that the mirror universe would behave exactly like our own. Then there's time reversal, or T. This is the concept of running the film of the universe backwards. Eggs would unscramble and leap back onto the table, smoke would pour back into a cigarette, and gravity would seem to push things upward. It's the ultimate thought experiment in reversibility. Individually, each of these symmetries was thought to be unbreakable. But in the 1950s, a shocking discovery was made by physicists Tsung-Dao Lee and Chen-Ning Yang. They proposed that the weak nuclear force, which is responsible for radioactive decay, might actually violate parity symmetry. This was soon confirmed in a beautiful experiment by Qin-Sheng Wu. She observed the decay of cobalt-60 atoms which emit electrons. In our universe, these electrons were emitted preferentially in one direction, but in the mirror universe they would be emitted in the opposite direction. The law of physics was not the same. The mirror world would actually behave differently from our own. parity was broken, not long after it was found that the weak force also violates charge conjugation symmetry on its own. And while most laws are time reversal symmetric at a fundamental level, some rare particle decays also show a slight preference for moving forward in time. So individually, C, P, and T are all broken, but here's the breathtaking part. If you perform all three operations together, if you create a universe that is simultaneously mirrored, made of antimatter, and running backwards in time, the laws of physics snap back into perfect alignment. This combined CPT transformation always gives you back a universe that is completely indistinguishable from the original. It is the ultimate cosmic reset button. This isn't just a curious observation, it's deeply woven into the very fabric of reality through two of the most important principles in physics, Lorentz invariance and the spin statistics theorem. Lorentz invariance is the cornerstone of Einstein's special relativity, stating that the laws of physics are the same for all observers moving at constant velocity. For this to hold true across the entire universe, CPT symmetry must also be true. The two are inextricably linked. Furthermore, the spin statistics theorem, which dictates that particles with half-integer spin are fermions and obey the Pauli exclusion principle, while integer spin particles are bosons and can pile on top of each other, also requires CPT symmetry to be valid. It is a foundational pillar that holds up our entire understanding of the quantum world. The experimental evidence for this symmetry is among the most precise in all of human science. We can't actually flip the entire universe into antimatter and run time backwards, but we can make incredibly precise comparisons between particles and their antiparticles. For example, we know the mass of a proton and an antiproton are identical to at least 1 part in a billion. Their electric charges are exactly opposite and equal in magnitude. Their magnetic moments are identical. We have compared the energy levels of hydrogen and antihydrogen atoms, and they show no measurable difference. If CPT symmetry were violated even in the tiniest way, these properties would not match so perfectly. The fact that they do is a powerful testament to this hidden symmetry's rule over reality. The implications of CPT symmetry are staggering. It suggests that an antimatter universe running backwards in time would be physically identical to our own. It also provides one of the strongest arguments for why antimatter must exist. The symmetry demands it. If we ever found a single, definitive experiment that showed a violation of CPT, it would force a complete rewrite of modern physics, challenging both quantum mechanics and relativity. So far, it has withstood every test, standing as a silent, unbreakable law that ensures the profound and hidden order of our cosmos remains intact. Yet for all the perfect balance that CPT symmetry demands, our universe presents us with a glaring and fundamental imbalance, one of the greatest mysteries in all of cosmology. We live in a world made almost entirely of matter. This is the puzzle of Baryon asymmetry. According to everything we understand about the Big Bang, energy should have condensed into equal amounts of matter and antimatter in those first fiery moments. Particles and antiparticles should have annihilated each other in a flash of gamma rays, leaving behind a cosmos filled with nothing but light. And yet, here we are. For every billion particles of antimatter that were created, there were 1,000,000,001 particles of matter. That 1 part in a billion excess is what survived the annihilation to form every single galaxy, star, planet, and person we see today. The question is, what broke the perfect symmetry? In 1967, the brilliant Russian physicist and dissident Andrei Sakharov provided the theoretical blueprint for how this could happen. He proposed that 3 specific conditions must be met for a matter-dominated universe to emerge from a perfectly symmetric beginning. It was a monumental insight that still guides physicists today. The first of Sakharov's conditions is baryon number violation. Baryons are a class of particles that include protons and neutrons, the building blocks of atomic nuclei. In our standard model of particle physics, the total number of baryons is conserved. You can't just create or destroy a proton out of nothing. But Sakharov realized that for an asymmetry to be generated, this rule had to be broken. There had to be a process in the early universe that could actually change the net number of matter particles over antimatter particles. Think of it like a cosmic ledger that started at zero. For the ledger to end up with a positive balance of matter, there needed to be a physical process that could actively add a credit or subtract a debit, something that could fundamentally change the bottom line. His second condition is a violation of both C and CP symmetry. We already know the weak force violates these symmetries individually, but Sakharov argued this was essential. If nature treated matter and antimatter exactly the same way during these early universe processes, any baryon number violation would simply create equal amounts of matter and antimatter, perfectly cancelling out any net gain. There had to be a physical process that differentiated between the two, that treated a particle slightly differently from its antiparticle, providing a directional bias. It's like a coin that is ever so slightly weighted. If you flip it 1 billion times, that tiny bias will eventually result in a measurable excess of heads over tails. CP violation is that tiny weighting in the fundamental laws of physics. The third and final condition is that these processes had to occur out of thermal equilibrium. In the searing, dense heat of the very early universe, everything was in a state of perfect thermal equilibrium, a frantic, chaotic soup where particles were constantly colliding and being created and destroyed. In such a state, any asymmetry generated by the first two conditions would immediately be wiped out by the reverse reactions. It would be like trying to fill a bucket with water while it has giant holes in the bottom. For the asymmetry to stick, to be preserved and not erased, the universe had to undergo a sudden change, a phase transition that pushed the system out of that balanced soup. This would be like rapidly cooling the system, freezing the asymmetry into place before the reverse processes could undo it. The expansion of the universe itself provided this crucial cooling, creating a brief window where the reactions could run more efficiently in one direction than the other. The big question is, did our universe actually meet all three conditions? We have observed CP violation in the decays of certain particles in laboratory experiments, so we know the second condition is possible. The expanding, cooling early universe certainly provided the out-of-equilibrium environment for the third condition. The real hunt is for the first one, a confirmed process that violates baryon number. Some grand unified theories which attempt to merge the electromagnetic, weak and strong forces predict such processes where protons could decay into lighter particles, but we have never observed it. Other ideas involve processes in the extreme conditions right after the Big Bang. The mystery remains wide open, a silent testament to that 1 in a billion event that made our existence possible. But the mathematical elegance of these Calabi-Yau shapes holds an even deeper and more astonishing secret, one that reveals a truly hidden symmetry at the very heart of string theory's geometry. This is the concept of mirror symmetry, and its implications are so profound they have revolutionized not just physics, but the field of pure mathematics itself. The idea is both simple and utterly mind-bending. Imagine you have two Calabi-Yau manifolds that look completely different from a geometric standpoint. One might have a certain number of holes or a specific complex pattern of curves and folds. The other could appear to be its polar opposite, with a wildly different topological structure. Perhaps it has hundreds of holes where the first has only a few. To a geometer studying their shapes, these two objects will be considered entirely distinct, with no obvious connection between them. Yet, mirror symmetry proposes that these two vastly different geometric shapes are in fact perfect mirrors of one another. They are two different geometric representations that describe the exact same physical universe. For the string theorist, this means the physics is identical. The way strings vibrate and propagate through one Calabi-Yau manifold produces the exact same spectrum of particles and forces as if they were vibrating through its mirror partner. It's as if the universe offered us two completely different user manuals, written in two alien languages that somehow provide identical instructions for building reality. This isn't just a curious observation, it's a powerful duality that provides physicists with an incredible calculational tool. Some calculations that are incredibly difficult to perform on one Calabi-Yau manifold become astonishingly simple when translated to its mirror partner. This is where the magic really happens, particularly in a branch of mathematics called enumerative geometry. This field is concerned with counting the number of geometric objects that can fit within another geometric shape under certain conditions. A classic, simple example is asking, how many lines can you draw through 2 points? The answer is straightforward, 1, but the questions get exponentially more difficult. A famously hard problem was to calculate how many rational curves a specific type of complex, winding curve of a given degree could fit within a particular Calabi-Yau shape. For centuries, mathematicians struggled with this. The number of curves of degree 3 was known to be 2,835, but the calculation for degree 4 was so complex it stumped experts for decades. Then, physicists using mirror symmetry arrived on the scene. They weren't trying to solve a math problem, they were calculating something for string theory called the Yukawa couplings, which determine how particles interact. To do this on one complicated Calabi-Yau, they used its simpler mirror partner. In the process of their physics calculation, they effortlessly generated the numbers that mathematicians had been desperately seeking. The answer for curves of degree 4, the physicists' calculation spit out the number 6,820,486,899. The mathematical community was both stunned and electrified. A deep problem in pure mathematics had been solved not by a mathematician, but by a physical duality between two six-dimensional shapes. This incredible cross-pollination between physics and math shows that mirror symmetry is far more than a nifty trick. It points to a fundamental redundancy in our description of reality. The universe seems to be telling us that there is no single, unique geometric language for its laws. Two completely different geometric foundations can lead to the exact same physical phenomena. This forces us to reconsider what we mean by the shape of the hidden dimensions. It may be that the true, fundamental description of reality is not geometric at all, but exists in a more abstract mathematical realm beyond our conventional intuition of space and form. The mirror pairs are simply two different shadows that this true reality casts onto the wall of our perception. And this remarkable idea of self-similarity, of patterns repeating across scales, takes us from the abstract mathematics of conformal field theory into the very fabric of the cosmos with our next concept, the possibility that the universe itself is fundamentally fractal. This is the theory of scale invariance, proposing that the same geometric and physical principles might be at work from the smallest quantum realms to the vast, sweeping structures of the cosmic web. It suggests a hidden symmetry not just in the laws but in the very architecture of reality. We see this echoed throughout nature in stunningly beautiful ways. A coastline from space, a head of broccoli, the branching of our own lungs, all exhibit this property of self-similarity, where a small piece of the object resembles the whole. But what if this wasn't just a curious feature of complex systems on Earth? What if it was a fundamental principle of the universe? Astronomers mapping the large-scale structure of the cosmos have found something astonishing. Galaxies are not scattered randomly through space like stars in the night sky. Instead, they are arranged in a colossal web of filaments and nodes with vast, empty voids in between. This cosmic web, when viewed in its entirety, bears an uncanny resemblance to the neural networks of a brain or the intricate structure of a fractal. Filaments of galaxies millions of light-years long are composed of smaller clusters which themselves are made of individual galaxies. Zoom in on a single galaxy and you find it is a fractal-like spiral of stars. Zoom into a star system and you might find a ringed planet, its rings composed of countless particles. The pattern seems to reiterate itself, suggesting a universe built on a principle of recursive complexity. This symmetry across scales becomes even more provocative when we consider the very small. The quantum foam, the seething, turbulent energy of spacetime at the Planck scale, is theorized to be a chaotic dance of virtual particles popping in and out of existence. The fluctuations in this quantum energy are thought to have been the seeds for all structure in the universe. Tiny, random variations in density in the early universe were stretched to enormous sizes by cosmic inflation, eventually becoming the gravitational wells that pulled matter together to form those very galaxies and galaxy clusters. In a very real sense, the largest structures we can observe, filaments hundreds of millions of light-years across, were born from quantum fluctuations smaller than a proton. The imprint of the microcosm is written across the macrocosm, a breathtaking connection between the smallest possible scale and the largest. This has led some physicists to propose theories that formally embed scale invariance into the laws of physics themselves. The Standard Model, as powerful as it is not scale invariant. Its forces behave differently at different energy levels. The strong nuclear force, for instance, gets weaker at shorter distances, a property called asymptotic freedom. But some beyond the Standard Model theories, including certain approaches to quantum gravity, seek to restore this symmetry. They propose that at the very highest energies, perhaps at the moment of the Big Bang, the universe was perfectly scale invariant. The laws of physics would have looked exactly the same regardless of the energy or distance scale you were observing. As the universe cooled and expanded, this perfect symmetry was broken, much like the way a perfectly symmetric seed crystal breaks symmetry as it grows into a unique snowflake, giving us the diverse and complex forces we see today. The implications are profound. A scale-invariant universe is one without a fundamental length scale. There is no preferred size for reality. It suggests that the universe could be structured in a deeply holistic way, with every level of organization informing the others. It might even provide a new perspective on the long-sought theory of everything, suggesting that the key is not to find the single fundamental particle or force, but to understand the pattern that connects all scales of existence. This fractal view of the cosmos presents a vision of a universe that is not just symmetrical in its laws, but symmetrical in its very form, a truly hidden and beautiful order repeating from the quantum void to the galactic supercluster. But the most radical reimagining of all suggests that the smooth, continuous stage of spacetime we take for granted, the very fabric of the universe, might itself be an illusion. This is the theory of emergent spacetime, a concept proposing that space and time are not fundamental building blocks of reality, but are instead collective phenomena that arise from the interactions of countless more basic quantum entities. Think of it like the fluidity of water. A single water molecule isn't wet, it doesn't flow, and it has no temperature or wave. These properties don't exist at the microscopic level. But when you bring trillions upon trillions of these molecules together, interacting and colliding with one another, the familiar properties of a liquid suddenly emerge. Fluidity, turbulence, and waves are not inherent to the molecules themselves. They are collective behaviors of the whole. In the same way, theorists propose that the four-dimensional continuum of spacetime might be a similar emergent property, bubbling up from a vast network of quantum information or a sea of entangled connections. So what are these more basic entities from which spacetime is woven? One of the most compelling candidates is quantum entanglement. We often think of entanglement as a bizarre connection where two particles share a fate, instantly influencing each other no matter the distance. But its role might be far more profound. It's been suggested that spacetime itself is actually woven together by these threads of entanglement. Imagine a vast, abstract network where each point is connected to others not by physical distance, but by their quantum information being intertwined. The strength of the entanglement between any two points would then determine their apparent proximity in the emergent spacetime. Two points that are highly entangled would appear to be close neighbors, while points with weak or no entanglement would seem vastly far apart. In this view, the geometry of space, its curvature, and even its very existence is a direct consequence of the pattern of quantum connections. This idea is so powerful that physicists have derived formulas directly relating the amount of entanglement between two regions of space to the area of the boundary separating them, a clear echo of the holographic principle we discussed earlier. Another approach suggests that the fundamental stuff of reality might be simple, abstract bits of information, like the ones and zeros in a computer. The physicist John Archibald Wheeler famously summarized this with the phrase "it from bit," proposing that every particle, every force field, and ultimately every facet of existence derives its properties from binary answers to yes or no questions. In this digital physics view, spacetime emerges from the processing of this cosmic information. The smooth continuity of space would then be a large-scale approximation, much like a digital photograph appears smooth and continuous from a distance but reveals its discrete pixelated nature when you zoom in closely enough. At the unimaginably tiny Planck scale, the universe might be fundamentally grainy, a seething network of informational relationships, and the symmetries we observe, like Lorentz invariance, which ensures the laws of physics are the same for all moving observers, would not be input into the system but would themselves be emergent properties. They would be the natural, stable state that arises from the chaotic interactions of these fundamental information bits, a hidden order born from complexity. This process of emergence would be governed by its own set of profound symmetries. Just as the laws of fluid dynamics are symmetric under rotations and translations, meaning a wave in the ocean behaves the same way no matter which direction it's moving or where it is, the laws governing the emergence of spacetime would possess deep symmetries that ensure the resulting stage is stable and consistent. These are not the symmetries of particles or forces, but the symmetries of the emergence process itself. They would dictate how countless microscopic quantum events conspire to create the reliable, predictable macroscopic reality we experience. This explains why our universe appears so continuous and lawful on human scales, even if it is fundamentally discrete and information-based at its core. The emergence process smooths out the underlying chaos, giving rise to the symmetrical and dependable arena in which stars are born and galaxies spin. It suggests that the deepest laws of nature might not be about things moving through space and time, but about the rules of organization that allow space and time to crystallize into existence in the first place. While the idea of emergent spacetime reimagines the stage of the universe as a collective phenomenon, another brilliant physicist reimagined the very nature of the lines we draw on that stage. Enter renowned mathematician and Nobel laureate Roger Penrose and his profoundly innovative creation, twistor theory. This is not just another take on quantum gravity, it's a complete inversion of our conventional perspective on reality. In our standard view, we start with spacetime, a four-dimensional continuum of points and events, and we then define particles and fields as things that exist within this arena. Penrose's radical proposal flips this entirely on its head. What if the most fundamental objects aren't the points in space and time, but something else entirely? What if spacetime itself is a secondary, derived concept that emerges from a more primitive and deeply geometric reality? That more fundamental reality, in twistor theory, is the world of twistors. Think of a twistor not as a thing located in space and time, but as a holistic object that actually defines a relationship between energy, momentum, and angular momentum, the intrinsic spinning of a particle. In a sense, a twister is a representation of a light ray, but it encodes not just the path of that light ray through the universe, but also its polarization, its spin, and its energy. A single twister defines an entire history. The breathtakingly elegant twist is that a point in our familiar spacetime is no longer a fundamental building block. Instead, a point is defined by the family of all light rays that pass through it. In the twister picture, a point in space is a secondary construction, a result of the intersection of countless more primitive twister lines. This profound shift in perspective brings immense hidden symmetries to the forefront, making previously intractable problems suddenly simple and beautiful. The description of massless particles like photons of light or hypothetical gravitons which always travel at the speed of light becomes remarkably elegant in the twister framework. Describing the scattering of such particles in conventional quantum field theory involves enormously complex calculations with thousands of terms that mostly cancel each other out. But when these same processes are translated into the language of twister geometry, the calculations simplify dramatically. The messy Feynman diagrams condense into elegant geometric figures, and the answers seem to almost fall out naturally from the mathematics. It's as if twister theory is speaking the native language of massless particles, a language where the inherent symmetries of light are built directly into the grammar. We can visualize these concepts through a powerful diagrammatic representation. Imagine a standard two-dimensional plane representing a slice of our complex spacetime. Now, instead of marking points on this plane, we draw lines, each line representing a light ray and, by extension, a twister. A point in this spacetime is then represented by a circle or a conic section that is the intersection of all the lines that pass through that point. The geometry becomes a dance of lines and curves, revealing relationships that are completely hidden in the standard point-based view. These twister diagrams aren't just pretty pictures, they are rigorous mathematical tools that allow physicists to calculate probabilities for particle interactions with a clarity and geometric intuition that was previously impossible. They reveal a deep connection between the quantum behavior of particles and the classical geometry of spacetime, suggesting that the quantum world might be far more geometric than we ever suspected. The implications of this are vast. Twister theory provides a completely different pathway toward unifying general relativity with quantum mechanics, one that prioritizes these profound geometric symmetries over the traditional quantum fields. It suggests that the quantum uncertainty and non-locality that so confound our standard models might be natural features of this twister-based foundation. While the full development of twister theory into a complete theory of quantum gravity remains a work in progress, its power as a calculational tool and its profound reimagining of what is fundamental continue to inspire physicists. It stands as a testament to the idea that sometimes the key to unlocking the universe's deepest secrets isn't to dig deeper into the structure we know, but to step back and ask if we're looking at the problem from the right direction at all. Yet if twister theory redefines our perspective on spacetime itself, another profoundly ambitious idea attempts to unify every single force and particle within a single, breathtakingly beautiful geometric object. This is the theory centered on the E8 Lie group, one of the most complex and exquisite structures in all of mathematics, and its controversial proposal to be the ultimate symmetry of the universe. To grasp the sheer scale of this idea, we first need to understand what a Lie group is. In mathematics, a group is a collection of objects that can be combined in a way that follows certain symmetrical rules. A Lie group is a special kind that is also a smooth, continuous manifold, a shape you can glide over. The simplest example is a circle. You can rotate a circle by any angle and it looks exactly the same. It possesses a perfect rotational symmetry. Now imagine vastly more complex shapes existing in many more dimensions, whose symmetries are so rich they can describe not just simple rotations, but the intricate dances of subatomic particles. The E8 group is the largest and most intricate of the 5 exceptional Lie groups. It is a monster of symmetry, a 248-dimensional shape of unimaginable complexity. To say it's abstract is an understatement. It's like a cosmic diamond with 248 perfectly symmetrical facets. Each point on this magnificent geometric object represents a different symmetry transformation. For a physicist, this isn't just beautiful math, it's a potential toolkit. The standard model of particle physics is itself built on smaller Lie groups U1 for electromagnetism, SU2 for the weak force, SU3 for the strong force. The dream of grand unification is to find a single, larger group that contains all of these within it, a master symmetry from which all forces naturally emerge. E8 is a prime candidate because it is large enough to contain the standard model and then some, potentially encompassing gravity as well. In 2007, a physicist and surfer named Garrett Lissy unleashed a storm of controversy when he published a paper titled An Exceptionally Simple Theory of Everything. Lissy's audacious proposal was to place every known elementary particle, the electrons, quarks, neutrinos, photons, gluons, and even the graviton, the hypothetical particle of gravity, onto this E8 geometry. He assigned each particle and force carrier to a specific point or root within the E8 root system. In this scheme, the bewildering zoo of particles wasn't a random collection. They were all just different facets of this single underlying geometric jewel. The way these points related to each other through the symmetry of E8 would then dictate how the particles interact, potentially predicting all the laws of physics in one elegant framework. The visual representation of the E8 root system is a thing of hypnotic beauty. It's often depicted as an 8-dimensional pattern projected down to 2 dimensions, resulting in an intricate, flower-like structure of concentric circles interconnected by a web of lines. It looks less like a physics diagram and more like a sacred mandala or a snowflake designed by a god. Each point where lines intersect represents a particle, and the lines connecting them represent their possible interactions. Lissy's model suggested that the seemingly random charges and properties of particles were actually fixed, necessary consequences of their specific location within this cosmic pattern. It was a vision of breathtaking unity where the universe's complexity was reduced to pure geometry. However, the physics community responded with intense skepticism, and for several critical reasons. The most glaring issue was the theory's treatment of gravity. While Lissy's model included the graviton, it did not successfully incorporate Einstein's general relativity in its full, non-linear glory. Reproducing the well-tested, intricate equations of gravity from such a framework is a monumental hurdle that the proposal did not clearly overcome. Furthermore, the model struggled with the concept of chirality, the observed handedness of the universe. The weak force, for instance, interacts only with left-handed particles, a fundamental asymmetry that is baked into the standard model. The raw E8 symmetry in its purest form is too perfect. It doesn't naturally prefer left over right, making it difficult to explain this observed feature of our world. Another major challenge was the lack of a clear mechanism for how the 3 dimensions of space and one of time that we experience emerge from this abstract, high-dimensional structure. Why would an 8-dimensional symmetry group produce a 4-dimensional spacetime? This problem of dimensional reduction is a common one in unification theories, but it remains a significant obstacle for the E8 proposal. Despite these formidable challenges, Lissy's work ignited public imagination and sparked renewed interest in the potential of exceptional mathematical structures to describe nature. It serves as a powerful reminder that the search for unity in physics often leads us to the most beautiful and complex corners of mathematics, and that the ultimate theory, if it exists, will likely be written in a language of profound and hidden symmetry. But what if this quantum strangeness isn't the final word? What if the seeming randomness of the quantum world is actually governed by a deeper, hidden layer of reality, a layer of perfect order and symmetry we simply can't directly observe. This is the tantalizing promise of hidden variable theories, which propose that particles do have definite properties all along, and that the unpredictability of quantum mechanics is just a veil obscuring a much more deterministic and perhaps more beautiful cosmic order. The most famous of these is Bohmian mechanics, also known as the de Broglie-Bohm pilot wave theory. This theory boldly restores a sense of classical intuition to the quantum realm. It proposes that every particle, like an electron, does indeed have a perfectly well-defined position and trajectory at all times. It's not a fuzzy probability cloud, it's a real thing with a real path. But how does it then produce the interference patterns we see in the double-slit experiment? The answer is a hidden, guiding influence, the quantum pilot wave. Imagine a particle is like a tiny boat being carried along by a wave. The wave itself is the wave function from quantum mechanics, spreading out and interfering with itself, creating a complex landscape of peaks and troughs. The particle doesn't randomly choose a path. It's passively guided along by this wave, inevitably following the channels carved out by the wave's interference. The particle has a hidden variable, its precise position, and the wave has a hidden variable, its form. Together, they create the illusion of randomness because we can't see the intricate details of the guiding wave. This theory is profoundly non-local, meaning the guiding wave can instantly influence the particle no matter the distance, a feature that many find as strange as the randomness it seeks to replace, but it does offer a picture of a universe with a hidden, deterministic symmetry beneath the quantum noise. For decades, this was a philosophical debate without a way to test it. Then, in 1964, the brilliant physicist John Stuart Bell devised a way to settle the argument experimentally. Bell's theorem created a precise mathematical inequality, a test that would distinguish between the world of standard quantum mechanics and any universe that obeyed local realism. Local realism is the very reasonable idea that objects are only influenced by their immediate surroundings, locality, and that they possess definite properties whether we measure them or not. Realism. It's the worldview of hidden variable theories, like a local version of Bohm's. Bell showed that if local hidden variables were real, then the results of certain measurements on entangled particles would have to satisfy his inequality. They would be bounded by a certain limit, but quantum mechanics boldly predicted that these same measurements would violate Bell's inequality, showing stronger correlations than any local hidden variable theory could ever allow. The experiments began, most famously by Alain Aspect and his team in the 1980s. They created pairs of entangled photons and sent them flying off in opposite directions to detectors that could measure their polarization. The crucial element was that the settings on these detectors were changed at the very last nanosecond, after the photons had begun their journey, preventing any signal traveling at the speed of light from one detector to the other to coordinate the result. The outcome was resounding and world-shaking. The experiments consistently showed a violation of Bell's inequality. The correlations between the entangled particles were stronger than any local, realistic theory could explain. Nature had voted, and the result was a clear no. There are no local hidden variables. The universe is not secretly playing by those simpler, more intuitive rules behind the scenes. This has staggering implications for the fundamental symmetries of nature. It tells us that the connectedness we see in quantum entanglement is a real, physical feature of the universe, not a sign of our ignorance of some deeper mechanism. This non-locality is a profound and hidden symmetry in its own right, a symmetry of connection that transcends space itself. Two particles can be instantaneously linked in a way that defies our classical understanding of cause and effect, acting as a single, unified entity regardless of the light years between them. The violation of Bell's inequality suggests that the universe is not just subtly weird, it is profoundly and fundamentally non-local. What happens here can be instantly connected to what happens there without any signal passing through the space in between. This doesn't allow for faster-than-light communication in a useful way, but it does force us to radically rethink the nature of reality itself, pointing toward a cosmos that is far more deeply and mysteriously interconnected than we ever dreamed. But this profound interconnectedness revealed by quantum mechanics leads us to a question that has haunted physicists and philosophers for generations. Why does our universe seem so perfectly tailored for life? The fundamental constants of nature, the strength of gravity, the mass of an electron, the precise value of the cosmological constant appear to be exquisitely fine-tuned. If any one of these values were even slightly different, atoms would not form, stars would not ignite, and life as we know it would be impossible. This cosmic coincidence has led some to propose a truly staggering idea. What if our universe is just one of countless others, each with its own unique set of physical laws and symmetries? This is the multiverse hypothesis, and it offers a radical explanation for fine-tuning through a principle known as the anthropic selection effect. The logic behind the anthropic principle is simple yet profound. We can only observe a universe that is capable of producing observers. If the multiverse is vast enough, containing every possible permutation of physical constants, then it is no surprise that we find ourselves in one of the rare habitable bubbles where the numbers just happen to line up correctly. In this view, there is no deeper reason or designer. We simply won the cosmic lottery. The apparent fine-tuning is not evidence of purpose, but a consequence of our own existence as observers who can remark upon it. One of the most compelling mechanisms for generating such a multiverse is the theory of eternal inflation. Picture the very fabric of spacetime during the Big Bang as a vast, bubbling cauldron of energy, an inflatened field. In most models of cosmic inflation, this field undergoes a rapid exponential expansion, smoothing and flattening our observable universe. But eternal inflation suggests this process never truly stops. The overall inflating background is like an endlessly boiling pot, and within it, random quantum fluctuations can cause localized pockets of this field to drop into a lower energy state. When this happens, the furious inflation inside that pocket ends, and that region crystallizes into a stable, expanding universe with its own unique physical properties, its own specific set of constants and broken symmetries. Our entire cosmos would be just one such bubble in an infinite, ever-growing froth of universes. Visualizing this is key to understanding its scale. Imagine an infinite ocean of pure, hyperactive spacetime expanding faster than the speed of light. Dotting this ocean are countless bubbles, each a separate universe. Some bubbles might be vast and long-lived like our own. Others might inflate for a moment before collapsing back into nothingness. Some might contain laws of physics where gravity is repulsive, or where electromagnetism is so strong that atoms cannot hold together. The variety is literally endless. In this cosmic landscape, the elegant symmetries we've explored, from supersymmetry to the specific form of the Calabi-Yau manifold, might not be fundamental necessities. They could simply be the local bylaws of our particular cosmic neighborhood, a random draw from a near-infinite deck of possibilities. The grand unified symmetry that we seek might be broken in a different way in every single bubble. This idea transforms the meaning of a fundamental theory of physics. Instead of predicting a single, unique universe, a truly fundamental theory would describe the entire landscape of possibilities, the multiversal menu from which each bubble universe makes its selection. The challenge, of course, is testability. If these other universes are forever beyond our observational horizon, separated from us by regions of space that are expanding faster than light, can we ever claim this is science? Proponents argue that the idea makes a testable prediction, that our universe should be one of the most probable ones that can support life. We should not expect to live in a universe that is maximally hospitable, but merely one that is minimally sufficient for our existence. Finding that our universe is, in fact, unusually bio-friendly compared to the strict minimum required could be evidence against the multiverse idea. Furthermore, if our bubble universe collided with another in the distant past, it might have left a detectable imprint on the cosmic microwave background, a faint circular bruise on the oldest light in the sky. While such evidence has been sought, nothing conclusive has been found, leaving the multiverse as one of the most spectacular and controversial ideas in modern cosmology, a grand symmetry of possibilities hidden just beyond the edge of everything we can see. While the multiverse concept stretches our imagination across countless cosmic bubbles, another profound theory brings our focus back to the very fabric of our own universe, proposing that space and time are not smooth and continuous, but are instead woven from a tapestry of discrete quantized threads. This is the core of loop quantum gravity, an approach that dares to dismantle the stage of spacetime itself and rebuild it from the ground up using a framework of breathtakingly beautiful geometric structures known as spin networks. Unlike string theory, which proposes that particles are tiny vibrating strings existing within a background spacetime, loop quantum gravity suggests that spacetime itself is the result of a more fundamental network of relationships. Imagine the universe not as a container but as a vast, evolving web. At each intersection of this web is a node representing a tiny, discrete volume of space. Connecting these nodes are links which represent the surfaces that separate these volumes. This is a spin network, a mathematical graph that encodes quantum information about the geometry of space itself. The spin in the name comes from the fact that each link is labeled with a number, a half-integer spin value much like the spin of an electron, which directly tells us the area of the surface it represents. The hidden symmetry here is deeply geometric and utterly fundamental. The network itself is a graph, and its structure, the way the nodes are connected, is not random. It possesses its own inherent symmetries related to how the graph can be transformed without changing the quantum state of space it describes. But the most profound symmetry is how this framework treats the very concept of space. In Einstein's general relativity, space is smooth and malleable, curving in response to mass and energy. Loop quantum gravity agrees that space is dynamic, but it posits that this smoothness is an illusion that emerges on large scales, much like a piece of fabric appears smooth from a distance but is actually woven from individual threads. At the tiniest possible scale, the Planck scale, space is granular. It is quantized. This leads to one of the theory's most stunning predictions, the quantization of area and volume. In our everyday world, you can theoretically cut an object in half again and again, forever getting smaller pieces. But loop quantum gravity says this is not true for space itself. There is a smallest possible unit of area and a smallest possible unit of volume. You cannot have half a unit of area, just as you cannot have half an electron. The area of any surface, from the event horizon of a black hole to the screen you're watching this on, is not continuous. It must be the sum of the discrete area quanta carried by all the spin network links that puncture that surface. Similarly, the volume of any region is the sum of the volume quanta associated with the nodes inside it. This means the universe is fundamentally pixelated, with the spin network defining the pixelation of reality. This network is not static, it evolves dynamically over time. The evolution of the spin network is described by a process that adds or removes nodes and links or changes their values. These discrete steps in time are governed by so-called spin foam models, which are like the history, or the movie, of the spin network changing. A spin foam can be visualized as a branching, frothy structure where the spin network slices represent individual frames. This provides a compelling way to reconcile the continuous flow of time we experience with the discrete, quantum nature of reality at the smallest scales. The smooth, curved spacetime of general relativity emerges from the collective behavior of this vast number of evolving quantum grains. much like the smooth flow of a liquid emerges from the chaotic motion of its trillions of molecules. The implications for understanding black holes and the Big Bang are revolutionary. For a black hole, the theory predicts that its event horizon is made of a finite number of these area quanta. This allows for a precise statistical calculation of the black hole's entropy, a measure of its internal disorder, which matches the famous result derived by Stephen Hawking decades earlier. This was a monumental success, providing a microscopic explanation for a property that was previously only understood through thermodynamics. Even more dramatically, because the theory eliminates the mathematical singularity where equations break down, it suggests that the Big Bang was not a true beginning from a point of infinite density, but rather a big bounce. In this scenario, a previous universe may have collapsed to a highly dense state before quantum gravitational effects became dominant, causing a rebound and the expansion of our own cosmos. The theory paints a picture of a universe that is not only deeply interconnected but also fundamentally finite and granular, revealing a hidden symmetry where the geometry of space itself is built from the quantum relationships between its most basic parts. Now let's step back from the most cutting-edge theories and return to a classic idea, one that first planted the seed for every modern concept of hidden dimensions. In 1919, a little-known German mathematician named Theodor Kaluza was reading Einstein's papers on general relativity, which described gravity as the curvature of the four-dimensional fabric of spacetime. Kaluza had a wild and brilliant thought. He wondered what would happen if he rewrote Einstein's equations not for 4 dimensions but for 5. When he did the math, something miraculous emerged. From the pure geometry of a 5-dimensional universe, Einstein's equations for gravity naturally appeared, but so did another, completely familiar set of equations, James Clerk Maxwell's equations for electromagnetism. In one breathtaking stroke, Kaluza had seemingly unified the two known fundamental forces of nature, not by inventing a new particle or field, but simply by adding an extra dimension of space. Gravity and light were revealed not as separate forces, but as different geometric aspects of a single, higher-dimensional reality. A few years later, Swedish physicist Oskar Klein refined this idea, providing a crucial answer to the obvious question: if there's a 5th dimension, where is it? Klein proposed that this extra dimension wasn't like the vast, extended ones we experience. Instead, it was curled up into an unimaginably tiny loop, a circle with a radius on the order of the Planck length, a scale so small that it's forever beyond our direct perception. This process is known as compactification. To understand this, imagine a garden hose stretched across a field. From a great distance, it looks like a simple one-dimensional line. But if you were an ant crawling on the hose, you would discover a second dimension, the circular direction around its circumference. In the same way, Klein suggested that at every single point in our familiar 4-dimensional spacetime, there is an attached, minuscule, circular 5th dimension. A particle moving through this 5-dimensional space would appear to us, trapped in 4 dimensions, to have a very specific property. Its momentum around that tiny circle would manifest as electric charge. The symmetry of this hidden dimension directly gave rise to the conservation of electric charge in our world. It was an idea of astonishing elegance and beauty, suggesting that the deepest laws of physics were, at their core, geometric and symmetrical. For decades, Kaluza-Klein theory remained a fascinating but somewhat forgotten footnote because it couldn't account for the other forces discovered later, like the strong and weak nuclear forces. But with the rise of string theory, this classic idea was not just revived. It was supercharged and transformed into the very engine of modern unification. String theory didn't just need one extra dimension. Its mathematics demanded 6 or 7 of them, all compactified into a complex multi-dimensional shape. The simple circle of Kaluza and Klein was replaced by the intricate Calabi-Yau manifolds we discussed earlier. Yet the core principle remained the same. the properties of the particles and forces we see are determined by the geometry of these hidden dimensions. The specific ways in which strings can vibrate as they move through and wrap around these compactified spaces define a particle's mass, its charge, and even what type of particle it is. We can actually visualize how these hidden dimensions might leave their imprint on our world. Think of a harp string. It can vibrate in different modes of fundamental tone and a series of higher harmonics. Each mode produces a different note. In a very similar way, a particle moving through a compactified dimension can also exist in different vibrational modes or harmonics. Each mode would appear to us as a different particle but with the same fundamental charge. This prediction leads to what is known as the Kaluza-Klein tower. For every fundamental particle, like an electron, there could theoretically exist an entire spectrum of heavier twin particles, each one corresponding to a higher harmonic vibration in the compactified space. These would be incredibly massive, which is why we haven't created them in our particle colliders yet. Finding evidence of such a Kaluza-Klein partner would be a direct detection of an extra dimension, a smoking gun for this profound hidden symmetry. The search for these particles is a major goal of next-generation colliders, a hunt for echoes from dimensions curled up into the very heart of reality. This brings us to a remarkable class of symmetries that operate not on particles or dimensions, but on the very forces that govern them. These are gauge theory dualities, a concept where two seemingly different descriptions of the universe's forces are revealed to be mathematically equivalent, two sides of the very same coin. This isn't just a neat trick, it's a powerful tool that allows physicists to solve problems once thought impossible, by translating them into a completely different language where the solution becomes almost obvious. The most classic and intuitive example of this is electric-magnetic duality. We all learn that electricity and magnetism are two aspects of the same electromagnetic force, described by Maxwell's elegant equations. But these equations possess a hidden, deeper symmetry. If you could magically swap every electric charge with a magnetic charge and simultaneously swap every electric field with a magnetic field, Maxwell's equations would look exactly the same. The universe would, in a very real sense, behave identically. The problem, of course, is that while we have plenty of electric charges in the form of electrons and protons, we've never found a fundamental particle that carries a magnetic charge, an isolated north or south pole, or a magnetic monopole. But if they did exist, this perfect symmetry would be a fundamental law of nature, revealing that electricity and magnetism are not just related, but are truly dual to one another. This idea was supercharged and generalized with the development of quantum field theories that describe the other forces, like the strong nuclear force. These are known as Yang-Mills theories, and they can be incredibly difficult to work with, especially when the force is very strong. Imagine trying to study the behavior of water by staring at a single, chaotic wave crashing on a shore. The details are a mess of foam and turbulence, but what if you could translate that problem into studying a calm, placid lake? You could learn everything you need to know about water much more easily, and then simply translate those calm water rules back to understand the crashing wave. This is the incredible power of a strong-weak duality. In the context of these quantum forces, strong and weak refer to the coupling constant, a number that represents how strongly the force's particles interact with each other. When the coupling is weak, physicists can use trusted approximation methods to calculate what will happen. It's like doing a simple physics problem with only a few variables. But when the coupling is strong, these methods completely break down. The interactions are so intense and complex that the math becomes a tangled, unsolvable knot. This is the infamous strong coupling problem, and it has long been a major roadblock in our understanding of the force that holds atomic nuclei together. S-duality, which is short for strong-weak duality, is the key that unlocks this problem. It proposes that a Yang-Mills theory with a very strong coupling constant is mathematically completely equivalent to a different Yang-Mills theory with a very weak coupling constant. They are dual descriptions of the same physics, so if you have a problem in the strongly coupled world that is impossibly difficult, you can use this duality to map it over to the weakly coupled world where it might be a simple calculation. You solve the easy problem there, and then you map the answer back to get the solution for the impossibly hard problem in the original theory. It's like finding a secret back door into a heavily fortified castle. The most powerful and well-studied arena for these dualities is in supersymmetric Yang-Mills theories. Supersymmetry, as we discussed earlier, provides just enough extra mathematical structure to make these incredible dualities precise and calculable without sacrificing the core physics. A flagship example is the duality discovered by physicist Nathan Seiberg and his collaborator Edward Witten. They were studying a particular supersymmetric version of the theory that describes the strong nuclear force. In the regime where the force becomes intensely strong, the standard mathematical tools were useless, but Seiberg and Witten discovered that this strong coupling theory was actually dual to a much simpler theory describing the behavior of magnetic monopoles, those elusive particles we mentioned before. This was a stunning revelation. The frantic, messy interactions of strongly coupled particles were somehow equivalent to the comparatively simple, classical motion of magnetic charges. Their work provided an exact map between these two worlds, giving physicists a complete solution to a theory that was previously thought to be unsolvable. The implications of this ripple far beyond a single calculation. These dualities reveal that our fundamental descriptions of nature might not be unique. What we perceive as a fundamental force might, in a different formulation, emerge from the behavior of completely different objects. It blurs the line between what is elementary and what is composite. In one description, an electron might be a fundamental point particle. In its dual description, it might be seen as a collective excitation of other entities. Much like a wave on the ocean is not a fundamental object but a behavior of countless water molecules. This tells us that the symmetries of the universe run deeper than we can directly observe, connecting disparate concepts through a hidden mathematical beauty that allows us to peer into the heart of strength itself. Roger Penrose's cosmic censorship hypothesis presents a stark and elegant rule for the universe, one that enforces a profound and hidden symmetry by dictating that the ultimate breakdown of physics must remain forever out of sight. At the heart of a black hole lies the singularity, a point of infinite density where the known laws of physics, including Einstein's general relativity, simply cease to function. It is a place where space and time themselves are torn apart, a mathematical monster that should, in principle, be visible to the universe. Penrose's brilliant conjecture acts as a cosmic referee, proposing that nature abhors a naked singularity. The hypothesis asserts that every singularity must be permanently cloaked or censored behind an event horizon, the one-way membrane from which not even light can escape. This isn't just a suggestion, it's a necessary law to preserve causality and predictability in our universe. Without this cosmic censor, the unpredictable, lawless chaos at a singularity could, in theory, influence the world outside, shattering our ability to understand cause and effect and making the future fundamentally unknowable. This idea is deeply intertwined with the laws of black hole thermodynamics, which themselves reveal a stunning hidden symmetry between gravity, heat, and quantum mechanics. The event horizon isn't just a prison wall, it's a surface with properties that eerily mirror those of a more familiar object. A black hole has a temperature, and it has entropy, a measure of its internal disorder. The larger the event horizon's area, the greater the black hole's entropy. This is a crucial symmetry. The surface area of the horizon directly corresponds to the information content hidden within. The second law of thermodynamics, which states that the total entropy of the universe always increases, finds a perfect partner in black holes. When matter falls in, the area of the event horizon increases, just as the overall entropy of the cosmos must always go up. This parallel suggests a deep, fundamental connection between the geometry of spacetime and the statistical laws of thermodynamics, as if gravity itself is a thermodynamic force. The cosmic censorship hypothesis acts as the guardian of this elegant system. If a naked singularity were to exist, it would represent a point of infinite temperature and infinite entropy, blowing a hole straight through the carefully constructed laws of thermodynamics. It would be a cosmic reset button with unpredictable results, a place where information could be both created and destroyed at will. By ensuring all singularities are hidden, cosmic censorship protects the sanctity of these thermodynamic laws, maintaining a beautiful symmetry between the macroscopic world of gravity and the microscopic world of quantum states. Ultimately, this ties directly into the most famous puzzle in modern physics, the black hole information paradox. If you throw a book into a black hole, the book is made of particles arranged in a specific, information-rich order. According to quantum mechanics, that information can never be truly destroyed. But according to classical general relativity, the book is lost forever behind the event horizon, its information seemingly erased from the universe when the black hole eventually evaporates via Hawking radiation. The cosmic censorship hypothesis doesn't solve this paradox, but it does contain it. By guaranteeing the singularity is always hidden, it prevents the information from being truly annihilated at that infinite point. The information might be scrambled, trapped, or encoded in some unimaginable way on the event horizon itself, as the holographic principle suggests, but it isn't destroyed in a way that would violate quantum law. The censorship ensures that the paradox remains a puzzle we can potentially solve with physics, rather than an absolute breakdown of reality that would leave us with no rules to follow at all. It is a hidden symmetry that, by imposing order on the most chaotic places in the cosmos, allows us to continue our search for a unified theory of everything. But hidden within the ghostly dance of the most elusive particles in the universe, we find another crack in the Standard Model's pristine symmetry, a subtle hint that the fundamental rules are even more complex than we imagined. This brings us to the enigma of neutrino oscillations, a phenomenon that forced us to rewrite our textbooks and revealed a profound, broken symmetry in the lepton sector. For decades, the Standard Model assumed that neutrinos, those barely their phantoms that stream through our bodies by the trillions every second, were massless. They were simply placeholders, chargeless spectators in the cosmic play. But then, experiments deep underground began to tell a different story. Detectors like Supersymmetry and in Japan and the Sudbury Neutrino Observatory in Canada were built to catch neutrinos coming from the sun and from cosmic rays interacting in our atmosphere. They discovered something astonishing. They were counting fewer neutrinos than expected. The neutrinos weren't disappearing. They were changing their identity right before our eyes, or rather, right before our detectors. This process is called neutrino oscillation. Neutrinos come in three distinct flavors, each paired with a charged lepton: the electron neutrino, the muon neutrino, and the tau neutrino. The groundbreaking discovery was that a neutrino born as one type could, as it travels through space, spontaneously morph into another. This is only possible if neutrinos have mass. If they were truly massless, as the original Standard Model demanded, they would travel at the speed of light and time would stand still for them from their own perspective. They would have no opportunity to change. The mere fact that they oscillate proves they have a tiny but non-zero mass. This was the first concrete, irrefutable evidence that the Standard Model is incomplete. A fundamental symmetry we had assumed was perfect had been broken. The mechanism behind this flavor-changing magic is a quantum interference effect that hinges on a mismatch between the flavor states and the mass states of the neutrinos. Think of it like this: the three flavors we detect, electron, muon, tau, are not the fundamental particles with definite mass. Instead, they are each a unique quantum mixture of three underlying mass states, each with a slightly different mass. As the neutrino hurtles through space, these three mass states evolve at slightly different rates due to their mass difference. By the time they reach our detector, they have fallen out of phase with one another, and when they recombine, the mixture has changed. The pure electron neutrino that left the Sun may now have a significant probability of showing up as a muon or tau neutrino when it arrives at Earth. This constant, silent transmutation is happening all around us, a hidden symmetry in motion, where identity is not fixed but is a fluid property that evolves over time. This broken flavor symmetry immediately begs the question: how do neutrinos get their mass in the first place? For other particles, like the electron, mass comes from their interaction with the Higgs field. But neutrinos are different. They are electrically neutral and only interact via the weak force and gravity, making them incredibly reluctant to engage with anything. The most compelling theory to explain their minuscule mass is the seesaw mechanism, an elegant idea that points toward a grander symmetry operating at an energy scale far beyond our current reach. The seesaw mechanism proposes the existence of an incredibly heavy, sterile neutrino, a right-handed partner to the known left-handed neutrinos. These hypothetical heavy neutrinos would not participate in the weak force at all, making them nearly impossible to detect directly. Their immense mass, perhaps 1 trillion times heavier than a proton, would act like an anchor on one end of a seesaw. As the anchor goes down the other end, the mass of the familiar light neutrinos we observe is levered up to an extraordinarily small value. The incredible lightness of our neutrinos is therefore a direct consequence of the incredible heaviness of their hidden partners. This isn't just a clever fix, it's a doorway to a deeper reality. The existence of these right-handed neutrinos is a key prediction of many grand unified theories and is deeply connected to the matter-antimatter asymmetry of the universe through a process called leptogenesis. In this scenario, the heavy sterile neutrinos would have been produced in the early universe and then decayed, violating CP symmetry and creating a tiny excess of leptons over anti-leptons. This lepton asymmetry could then have been converted into the Baryon asymmetry we see today through Sphaleron processes in the electroweak epoch. In this way, the faintest whisper of mass in the lightest known particles becomes our strongest clue to understanding why we, and everything made of matter, exist at all. The subtle broken symmetry of neutrino oscillations thus ripples outward, connecting to the most fundamental asymmetries of the cosmos and hinting at a majestic, hidden symmetry at a scale we can only dream of probing. Now, if we venture even further into the abstract, we encounter a class of theories so detached from conventional geometry that they're only concerned with the shape of spacetime itself. This is the domain of topological quantum field theories, or TQFTs. Imagine a theory of physics that doesn't care about distances, angles, or even the precise curvature of space. In a TQFT, the only things that matter are the global, topological properties, the number of holes in space, whether the universe is shaped like a sphere or a donut, or how different regions are knotted together. A TQFT is completely invariant under any smooth, continuous deformation of spacetime. You can stretch, twist, or bend the universe like rubber, and as long as you don't tear it or glue parts together, the physical predictions of the theory remain exactly the same. It's a framework where the rigid, metric-based rules of Einstein's gravity are replaced by a much more fluid and malleable set of principles. This profound indifference to local details makes TQFTs the perfect language for describing exotic new states of matter, particularly topological phases. In an ordinary material, the properties are determined by the pattern of atoms and the forces between them. But in a topological phase, the most important characteristics are global and robust. The most famous example is the fractional quantum Hall effect, observed when a two-dimensional electron gas is subjected to an incredibly strong magnetic field at temperatures near absolute zero. Under these extreme conditions, the electrons collectively organize into a new state where their behavior is no longer described by their individual identities, but by emergent quasi-particles dancing across the surface. What makes this state topological is its incredible stability. You can poke it, prod it, or introduce impurities, and its essential Hall conductance remains precisely quantized and unchanged. This robustness arises because the property is tied to a topological invariant of the system's electronic wave function, a kind of quantum number that can only take on certain integer values and cannot change without a fundamental phase transition. It's a physical property protected by the mathematics of topology itself. Within these topological phases, the most fascinating entities emerge: anyons. In our familiar three-dimensional world, fundamental particles are classified as either bosons or fermions. Bosons, like photons, can share the same quantum state, while fermions, like electrons, cannot. This is the Pauli exclusion principle that gives matter its structure. But in a two-dimensional system, a whole new world of possibilities opens up. Anyons are quasi-particles that defy this binary classification. When two identical anyons are swapped or braided around each other, their quantum wave function doesn't just pick up a simple plus or minus sign. Instead, it can be multiplied by any complex phase factor or even by a matrix, leading to a continuous range of statistics, hence the name anyon. This strange behavior is only possible because the two-dimensional plane allows for a richer set of paths particles can take when they orbit one another. The history of their braiding becomes a topological property of their world lines. This isn't just a mathematical curiosity, it's the foundation for a revolution in quantum computing. The biggest obstacle to building a practical quantum computer is decoherence, the tendency for fragile quantum states to be destroyed by the slightest noise or interaction with their environment. Topological quantum computation proposes a brilliant solution. Encode quantum information not in individual particles, but in the global topological properties of a system. Specifically, information would be stored in the braiding patterns of anyons. Because these patterns are topological, they are incredibly robust against local disturbances. A tiny jiggle or a minor imperfection in the material might slightly change the path of an anyon, but it won't change the overall topology of its braid. It's like writing a message in the form of a knot. You can shake the string, and the knot itself remains intact. Performing a quantum computation would then involve physically braiding these anyons around each other in a specific sequence, with the final result being read out by observing the system's topological state. This approach promises fault-tolerant quantum computation by its very design, turning the weakness of quantum fragility into a strength through the power of hidden symmetry. Yet for all the intricate symmetries we've explored, from the cosmic to the quantum, there remains one of the most pivotal and beautiful processes in all of physics: the moment a perfect symmetry breaks, giving rise to the diversity and structure of our world. This is the concept of spontaneous symmetry breaking, and its most famous consequence is the mechanism that gives mass to the fundamental particles, orchestrated by the now celebrated Higgs field. To understand this, picture a perfectly sharp pencil balanced exactly on its tip. This setup is exquisitely symmetrical. From every horizontal direction you look, the pencil looks identical. There is no preferred direction, but this state is also profoundly unstable. The slightest breath of air, the tiniest vibration, will cause it to topple over. When it falls, it must choose a random direction. In that moment, the perfect symmetry is broken. The pencil now has a specific orientation, and the symmetry that was once there is now hidden. The laws of physics that govern the pencil haven't changed. They are still rotationally symmetric, but the state the pencil is in has broken that symmetry. The universe, in a sense, has made a choice. The Higgs mechanism applies this same profound idea to the vacuum of empty space itself. In the searing heat just after the Big Bang, the universe was in a truly symmetric state. The Higgs field, which permeates all of reality, was zero everywhere. In this state, all fundamental particles, like electrons and quarks, were massless and zipped around at the speed of light. But as the universe expanded and cooled, it underwent a cosmic phase transition, much like water freezing into ice. The Higgs field could no longer remain at zero. It settled into a new, stable state everywhere throughout the cosmos. But just like the falling pencil, it had to choose a value. This everywhere present non-zero value is what we call the Higgs vacuum expectation value. This is where mass comes from. As particles move through the universe, they interact with this omnipresent Higgs field. Think of space not as a void, but as a vast, invisible ocean of Higgs molasses. Some particles, like photons, are like Olympic swimmers. They don't interact with the molasses at all and slice through it effortlessly, remaining massless. But other particles, like electrons and quarks, are like most of us trying to wade through water. They interact strongly with the field. This interaction is what we experience as mass. The more a particle feels the Higgs field, the heavier it is. The Higgs field doesn't so much give mass as it provides a resistance to acceleration. A particle's mass is essentially a measure of how hard it is to push it through this cosmic treacle. The excitement in the physics community reached a fever pitch in 2012 when the Large Hadron Collider at CERN announced the discovery of the Higgs boson. This particle is crucial because it is not the Higgs field itself, but rather a localized ripple in the Higgs field. Just as splashing in water creates water droplets, exciting the Higgs field with enough energy can create a Higgs boson. Its discovery was the smoking gun, confirming that this field and its symmetry-breaking mechanism were not just elegant mathematics but a real, physical component of our universe. It was the final piece of the Standard Model puzzle, a triumph of human prediction and experimentation. Yet for all its success, the Higgs mechanism leaves us with deep and troubling questions, primarily the problem of naturalness. The mass of the Higgs boson itself is incredibly fine-tuned. Quantum mechanics allows for virtual particles to pop in and out of existence, and these should contribute enormous amounts to the Higgs's mass, making it hundreds of millions of times heavier than what we observe. For it to remain at 125 times the mass of a proton, there must be a miraculous, perfect cancellation between these huge quantum contributions. It's as if you had an equation where two numbers, each in the billions, subtracted to give a result of 125. This seems absurdly unnatural, suggesting either a staggering cosmic coincidence or that there is physics beyond the standard model, like supersymmetry, that provides unseen particles to perfectly balance the quantum books and protect this delicate symmetry. The discovery of the Higgs boson was not an end, but a magnificent new beginning, pointing our inquiries toward the next layer of hidden cosmic order. But if the holographic principle and black hole thermodynamics reveal a hidden symmetry in information, and cosmic censorship protects the laws of physics from chaos, then what of the cosmos itself? Does it have a beginning and an end, or is it part of a grander, eternal cycle? This brings us to one of the most poetic and geometrically profound theories of all, Roger Penrose's conformal cyclic cosmology. This radical vision proposes that the universe is not a one-time event, but part of an endless sequence of cosmic eras, which Penrose calls eons. Each eon begins with its own Big Bang and expands outward for trillions upon trillions of years, ultimately fading into an unimaginably vast, cold, and empty void. But rather than ending in nothingness, Penrose's theory suggests that this empty expanse becomes the pristine, high-energy seed for the next Big Bang. The entire process is bridged by a breathtakingly beautiful and hidden symmetry, conformal invariance. To grasp this, we must first understand what happens at the very far future of our universe. All stars will eventually burn out, black holes will evaporate via Hawking radiation, and even protons are predicted to decay over immense timescales. After perhaps 10 to the power of 100 years, the universe will contain nothing but a sparse, ultra-cold soup of photons and other massless particles, all drifting infinitely far apart. In this state, the universe loses all sense of scale. There are no rulers or clocks left to measure distance or time. The concepts of here and there, now and then become meaningless. The geometry of this future universe becomes scale invariant or conformally invariant. It's like taking a vast, empty desert and being able to zoom in or out infinitely without any change in its appearance. At this point of maximum emptiness, the universe has, in a very real geometric sense, forgotten how to be big. Penrose's genius was to recognize that this conformally invariant end state is geometrically identical to the conformally invariant beginning of a universe. The hot, dense, and incredibly small singularity of a Big Bang also lacks any inherent scale. At those extreme energies, particles are effectively massless, and the physics is dominated by radiation, which itself is conformally invariant. So, through the strange magic of conformal geometry, the infinite future of one eon can be seamlessly attached to the Big Bang singularity of the next. The remote future of our universe becomes the nothing from which the next universe is born. This isn't a violent collision or a bounce in the traditional sense. It's a smooth, geometric identification where the end of time in one epoch simply becomes the beginning of time in the next. The two are different manifestations of the same conformally symmetric state. This elegant idea offers a stunning solution to one of the deepest puzzles in cosmology. Why did our universe begin in a state of such incredibly low entropy? The second law of thermodynamics tells us that entropy or disorder always increases. This is why we remember the past and not the future. But this law also implies that the universe must have started in an extraordinarily ordered, low entropy state, like a perfectly stacked deck of cards. The standard Big Bang model offers no explanation for this. It simply takes this highly improbable initial condition as a given. Conformal cyclic cosmology, however, provides a natural explanation. In Penrose's model, the gravitational entropy, the disorder associated with the arrangement of matter and spacetime itself, is effectively reset to zero at the crossover point between eons. When the universe expands to that vast, empty, conformally symmetric state, it is once again in a state of maximum smoothness and minimum gravitational entropy. This pristine geometric state then becomes the low entropy beginning for the next eon. The reason our universe started with such perfect order is because it inherited it from the perfectly smooth end of its predecessor. The most audacious part of Penrose's theory is that it might leave observable fingerprints in our universe today. He proposed that violent events from the previous eon, particularly the collisions of supermassive black holes, could have sent powerful shockwaves of gravitational energy across the conformal boundary into our own eon. Because the conformal rescaling changes the nature of energy, these immense gravitational waves would manifest in our early universe as spherical ripples of temperature variation in the cosmic microwave background, the faint afterglow of the Big Bang. Penrose and his collaborator, Vark-Gersadian, analyzed data from the WMAP and Planck satellites and claimed to have found concentric rings of strangely low temperature variance within the CMB, which they called Hawking points, theorized to be the imprints of black hole evaporation from the previous eon. This claim remains highly controversial within the cosmology community. Many scientists argue that these patterns could be the result of statistical noise or other astrophysical processes within our own universe. The search for conclusive evidence is ongoing, yet the profound beauty of conformal cyclic cosmology lies not just in its potential to be proven, but in the majestic vision it presents, a universe without beginning or end, an endless cycle of creation and dissolution, all governed by a hidden geometric symmetry that connects the void of one eternity to the fire of the next. It suggests that the ultimate fate of our cosmos is not a lonely freeze or a fiery crunch, but a transformation, a quiet return to a state of perfect symmetry, ready to begin the story all over again. But how does the fragile, probabilistic world of quantum possibilities resolve into the single, definite reality we all seem to share? If a quantum particle can exist in a blur of many states at once, why do we only ever observe one concrete outcome? This brings us to a fascinating theory that applies the logic of natural selection to the quantum realm, quantum Darwinism. This idea proposes that the emergence of a single, objective reality isn't a random collapse, but a process of environmental selection that favors certain quantum states and symmetries, weeding out others until a consensus is reached. To understand this, we need to revisit the infamous problem of quantum measurement. In the classic double-slit experiment, a single electron seems to pass through both slits simultaneously, interfering with itself like a wave. But the moment we place a detector to see which slit it goes through, this wave-like behavior vanishes and the electron appears to choose a single, definite path. The act of observation seems to force the particle to make a decision. For decades, this was the central mystery. Quantum Darwinism offers a powerful solution by shifting the focus from a mysterious collapse to a physical process called decoherence, amplified by the environment itself. Think of a quantum system like that electron as being incredibly shy and private. Its superposition, its existence in multiple states, is a fragile secret it keeps to itself. But this secrecy is impossible to maintain once it interacts with the outside world. The electron will inevitably bump into a few photons of light or molecules of air. With each collision, it imprints a tiny piece of information about its state onto the environment. It's like whispering your secret to one person after another. Very quickly, countless copies of this information are broadcast out into the surroundings. This process is decoherence, and it happens at an astonishing speed, effectively destroying the delicate quantum interference that allows for multiple realities to coexist. Now, here's where the Darwinian selection comes in. Not all quantum states are created equal when it comes to being copied. Some states are far more robust and stable when interacting with the environment. They are the fittest states, capable of being faithfully replicated over and over again without being distorted. These are known as pointer states. Other, more fragile states are quickly scrambled and lost in the environmental noise. They fail to produce surviving copies of their information. The environment acts as a selective pressure, favoring the pointer states and allowing them to proliferate. In this cosmic survival of the fittest, the states that can create the most copies of themselves in the environment are the ones that win. They become the objective reality because their information is now available for multiple observers to independently detect and agree upon. A simple analogy can make this clear. Imagine a sculpture made of ice in the middle of a desert. The sculpture has a specific shape, but the desert sun is relentless. The sculpture will melt and its water will evaporate, imprinting information about its composition into the atmosphere. But the desert doesn't record every intricate detail of the sculpture. It only preserves the most robust information, the fact that it was made of H2O molecules. The detailed artistry of the ice is lost, but the fundamental fact of its waterness is broadcast everywhere. Similarly, the environment doesn't record every possible quantum state of a particle. It selectively copies and propagates only the most stable, redundant information, the pointer states. This process creates what is called a witness consensus. You, I, and any other observer can each independently measure the same quantum system, and we will all agree on its properties. We all see the same pointer state. This isn't because we caused the collapse, but because we are all just accessing the same, widely broadcast information that the system has already deposited into the environment. The reason reality appears objective and classical is because the winning quantum states have been so thoroughly copied and disseminated that any observer can easily find the same data. The symmetry that has preserved the objective reality we all share is not an arbitrary choice but a naturally selected outcome of this continuous copying interaction with the world. Quantum Darwinism suggests that the solid world we perceive is essentially a quantum version of a meme that went viral, its information replicated so universally that it becomes the accepted truth of the universe. But for all the profound symmetries we've charted in the luminous universe of stars and particles, a far greater portion of reality remains shrouded in darkness, governed by rules we can only begin to guess at. This brings us to the enigma of dark matter and the tantalizing possibility that its elusive nature is protected by its own set of hidden symmetries, completely different from those that light up our own world. The evidence for dark matter is written in the very motion of the galaxies themselves. When astronomers measure how fast stars orbit the center of a spiral galaxy, they find something astonishing. According to the laws of gravity and the amount of visible matter we see, stars, gas, and dust, stars on the outer edges should be moving much more slowly. Instead, they are hurtling around at speeds that should fling them off into the void. The only explanation is that each galaxy is enveloped in a massive, invisible halo of something that provides the extra gravitational glue to hold it all together. We can map the shape of this halo by the effect it has on the paths of stars, revealing a vast spherical cloud of unseen mass that dwarfs the luminous galaxy at its heart. This dark matter doesn't seem to absorb, emit, or reflect light. It interacts with our world almost solely through the force of gravity. The question is, what hidden principles keep it so stable and so aloof? One elegant idea is that dark matter is part of a parallel cosmic sector, a kind of mirror universe governed by a symmetry that duplicates our own. This is the theory of mirror matter. It proposes that for every known particle in the standard model protons, electrons, neutrons, there exists a mirror counterpart. A mirror proton would have the same mass as our proton, but it would be completely invisible to us because it interacts only through its own set of mirror forces. A mirror photon would carry a mirror version of light that our eyes could never see. In this view, dark matter could simply be this mirror stuff, this shadow matter woven through our own space. The two sectors would share the same gravitational force, which is why the mirror matter in a galaxy's halo can pull on our stars, but they would be otherwise separate, like ghosts passing through a wall. A profound symmetry between the ordinary and mirror sectors would ensure the stability of dark matter. It would have its own mirror chemistry and physics, living out its existence almost entirely independent of our own, its particles rarely, if ever, decaying into anything we could detect. Perhaps the most scientifically popular candidate, however, arises from a symmetry we've already explored, supersymmetry. If SUSY is correct, then the lightest supersymmetric particle, or LSP, would be absolutely stable. This is due to a powerful conservation law called parity, which would prevent it from decaying into any of the lighter standard model particles. This particle, often thought to be the neutralino, would be electrically neutral and interact only through the weak nuclear force and gravity, making it incredibly difficult to detect. It would be a perfect WIMP, a weakly interacting massive particle permeating the universe in vast numbers since the Big Bang. The hidden symmetry of supersymmetry would therefore provide a natural, elegant explanation for both the stability of dark matter and its lack of interactions. It wouldn't be a separate, ad hoc invention. It would be a necessary and predicted piece of the cosmic puzzle, its existence and properties demanded by the mathematical beauty of the theory itself. The stability of these candidates is the key. For dark matter to have persisted for over 13 billion years, the particles that constitute it must be incredibly long-lived. Any symmetry that guarantees this stability is a prime candidate for governing the dark sector. This could be a conserved quantum number, akin to how electric charge is conserved in our world. If a dark matter particle is the lightest particle that carries a certain dark charge, then it has nothing lighter to decay into without violating the conservation of that charge. It would be trapped in its own state, forced to remain stable for all time, silently shaping the cosmos through gravity alone. Whether through the mirror symmetry of a parallel world or the supersymmetry of a unified particle family, the darkness that holds the galaxies together may be ruled by a hidden order just as elegant and profound as the one that gives us light. Yet for all the ghostly connection of quantum entanglement, the theory of general relativity offers a completely different kind of bridge through the fabric of spacetime itself. This brings us to one of the most mind-bending and beautiful conjectures in modern physics, a proposal that these two seemingly disconnected ideas are actually two sides of the same coin. This is the ER equals EPR hypothesis, a daring idea that suggests every pair of entangled particles is secretly connected by a microscopic wormhole. To understand this profound duality, we need to look back at two landmark papers from 1935, both authored by Albert Einstein and his colleagues. The first, with Boris Podolsky and Nathan Rosen, the EPR paper pointed out the bizarre, spooky action at a distance of quantum entanglement, where two particles can instantaneously influence each other no matter how far apart they are. The second paper, with Rosen alone, introduced the concept of an Einstein-Rosen bridge, or ER bridge, what we now commonly call a wormhole. This is a tunnel-like structure in spacetime that could, in theory, create a shortcut connecting two distant points in the universe. For decades, these two ideas lived in completely separate worlds. Entanglement was a property of the quantum realm, a connection without a mechanism. Wormholes were a fantastic prediction of general relativity, a geometric structure that most physicists believed was unstable and unusable. The revolutionary ER equals EPR proposal, most famously championed by physicists Juan Maldaisner and Leonard Susskind, boldly claims that these are not two different concepts, but two different descriptions of the exact same thing. An entangled pair of particles, like two electrons with perfectly correlated spins, are not mysteriously linked across a void. Instead, they are connected by a physical, albeit incredibly tiny, wormhole. The quantum connection is a geometric connection. This would mean that what we perceive as spooky action is actually a subtle manipulation of the very geometry of space, a distortion so minute we've never been able to detect it. It's a vision that begins to heal the great rift between quantum mechanics and gravity, suggesting that the laws of information in the quantum world are fundamentally about the structure of spacetime itself. This idea finds its most powerful expression in the context of black holes. Imagine two black holes that are maximally entangled with each other. According to the ER equals EPR conjecture, these two black holes would not be separate objects. They would be connected by the largest possible wormhole, a tunnel through spacetime often referred to as a non-traversable wormhole. You couldn't actually travel through it. Any attempt would result in the tunnel collapsing, but it would exist as a permanent geometric feature linking their interiors. This provides a stunningly elegant resolution to the black hole information paradox. Information that falls into one black hole doesn't disappear. It can exit through the wormhole connection via the other black hole's Hawking radiation. The information is never lost, it's just transferred through a hidden geometric channel, preserving the fundamental laws of quantum mechanics. The event horizons of the two black holes are, in a very real sense, the same surface connected through a higher dimensional space. This incredible proposition also offers a potential solution to one of the most terrifying puzzles in theoretical physics, the black hole firewall paradox. This paradox asks a brutal question: what would you experience if you fell into a black hole? The principles of general relativity, Einstein's masterpiece, provide a comforting answer. According to the equivalence principle, spacetime should be smooth everywhere. An astronaut crossing the event horizon should feel nothing special. It should be an uneventful, if ultimately doomed, passage. However, straightforward quantum mechanical calculations suggest the opposite. They indicate that the event horizon should be a raging inferno of high-energy particles, a deadly firewall that would instantly incinerate anything falling in. This is a catastrophic contradiction between our two most fundamental theories of nature. The wormhole symmetry of ER equals EPR elegantly dissolves this paradox. If the interior of the black hole is connected via a wormhole to the radiation it has already emitted, then the geometry at the horizon is not what we thought. The microscopic structure of spacetime is radically altered by these untold numbers of tiny wormholes linking the interior to the distant Hawking radiation. This complex wormhole-riddled geometry could smooth out the intense energy, preventing a firewall from ever forming. The astronaut would pass through the horizon unharmed, not because the quantum calculations are wrong, but because they didn't account for this profound modification of spacetime's architecture. The singularity remains the true danger, but the horizon itself is safe, preserving both the laws of quantum mechanics and the experience of the infalling astronaut. It's a theory that suggests the universe is not just stranger than we imagine, but that its deepest symmetries are woven into the fabric of connection itself, tying together the quantum and the cosmic in a single, breathtakingly elegant framework. But what if the very coordinates we use to map the universe, the x, y, and z of our reality, are not the reliable, bedrock foundations we believe them to be? This brings us to a theory that challenges the very alphabet of spacetime, proposing that at the most fundamental level, the order in which you measure things truly matters. This is the realm of non-commutative geometry, a profound framework where the fabric of space itself becomes fuzzy and quantized, governed by a strange and beautiful new kind of symmetry. To grasp this mind-bending idea, we can draw a direct analogy from the dawn of quantum mechanics. In our everyday classical world, multiplication is commutative. If you multiply 3 by 5, you get the same result as multiplying 5 by 3. The order doesn't matter, but in the quantum world, this basic rule breaks down for certain properties. The most famous example is the position and momentum of a particle. In quantum math, multiplying the position operator by the momentum operator does not give the same result as multiplying the momentum operator by the position operator. Their product depends on the order, they do not commute. This mathematical fact is the very reason for Heisenberg's uncertainty principle. You cannot know both the exact position and exact momentum of a particle simultaneously. The universe has a fundamental fuzziness built into its core. Non-commutative geometry applies this exact same quantum logic to spacetime itself. It proposes that the coordinates that label points in space, traditionally simple numbers that commute, should instead be treated as non-commutative operators, much like matrices. Imagine trying to pinpoint a location in this quantum space. You might have an operator for your north-south position and another for your east-west position. In this new framework, multiplying your north-south coordinate by your east-west coordinate would yield a different result than the reverse. The very concepts of here and there become blurred. There is now a fundamental uncertainty in locating a point in space, suggesting that below a certain scale, perhaps the Planck scale, the smooth continuum of spacetime dissolves into a granular, fuzzy foam. You cannot simultaneously know all your spatial coordinates with infinite precision. The universe resists being pinned down to a single, infinitesimal point. This radical rethinking of geometry was pioneered by the French mathematician Alain Connes, and it opens the door to a breathtaking unification of forces. In our standard physics, forces are described by fields that exist on a geometric stage of spacetime. Gravity is the curvature of that stage, but in non-commutative geometry, the stage and the actors on it become inseparable. The forces themselves are seen as natural consequences of the geometric irregularities, the non-commutativity of spacetime. The different fields of the standard model, the electromagnetic field, the Higgs field, the other force fields, are all generated from the internal vibrations and fluctuations of this non-commutative space. It's as if the particles and forces we see are not inhabitants of space, but are instead the very music of space itself, emerging from its underlying quantized harmonic structure. We can visualize this using a powerful analogy from matrix models. Think of a classic, smooth, curved surface like the exterior of a sphere. Now, imagine you want to approximate that smooth surface using a finite set of data points. You could create a grid of points and connect them, but a more profound method is to represent the entire geometry using a matrix. The eigenvalues of that matrix, a set of special numbers derived from it, can correspond to the possible positions in that space. The off-diagonal elements of the matrix describe how these different points are connected, creating a web of relationships. As you increase the size of the matrix to include more and more data, your approximation of the smooth sphere becomes better and better. But non-commutative geometry suggests that at the very bottom, reality isn't the smooth sphere, it's the matrix itself. The smooth geometry we experience is a large-scale, classical illusion that emerges from a vast, interacting network of these non-commuting elements. Space is not a container, it is a web of algebraic relationships. The implications for unification are staggering. This approach provides a natural mathematical language to describe the internal spaces that give particles their properties like charge and spin. In the standard model, these internal quantum numbers are tacked on somewhat awkwardly to the spacetime coordinates. But in non-commutative geometry, these internal degrees of freedom and the external spacetime coordinates are all part of one cohesive, non-commutative whole. The force of gravity, described by the geometry of spacetime, and the other forces described by these internal spaces, all find a common origin in the algebraic structure of a single master geometry. It suggests a universe where the forces are not just unified in a grand unified theory, but are geometrized, seen as inevitable expressions of a spacetime that is inherently quantum and algebraic from its very foundation. This isn't just a new theory of particles, it's a new theory of what space itself is, revealing a hidden symmetry where matter, energy, and geometry are finally and completely intertwined. But what if the relentless forward march of time, the very arrow that gives our universe its sense of past and future, is itself an illusion emerging from a deeper, more symmetrical reality? This brings us to a radical rethinking of quantum mechanics that restores a beautiful symmetry to time itself. The standard view of quantum evolution presents a stark asymmetry. A quantum system evolves smoothly and deterministically according to Schrödinger's equation until the moment it is measured. At that instant, the wave function is said to collapse, randomly selecting one of its many possible states to become our reality. This collapse is irreversible. It breaks the symmetry of time. You can run the film backwards up to the point of measurement, but the collapse itself only makes sense moving forward. This introduces a fundamental ambiguity. What exactly counts as a measurement? Is it a conscious observer, a large enough apparatus? The theory doesn't say. The two-state vector formalism, championed by physicists like Yakir Aharonov, offers a breathtakingly elegant alternative. It proposes that the quantum world is fundamentally time-symmetric. To determine the state of a quantum system at any given moment, you cannot simply look at its past. You must also consider its future. In this picture, a particle is described not by a single wave function evolving from the past, but by two wave functions, one evolving forward in time from a preparation event in the past, and another evolving backward in time from a measurement event in the future. The present reality is a kind of handshake between these two waves, a meeting point between what we traditionally call cause and effect. This doesn't require any mystical foresight. It means the equations of quantum mechanics work just as well running backwards as they do forwards, and the full description of a system requires both boundary conditions. This approach provides a stunningly clear resolution to the infamous measurement paradox. Consider the classic double-slit experiment with a twist, often called a quantum eraser experiment. A particle is sent toward two slits, and we place a device behind the slits that can tell, in principle, which path the particle took. According to standard quantum mechanics, this which path information should destroy the interference pattern, forcing the particle to behave like a single, localized object. But in the two-state vector view, the story isn't over. If we later erase that which path information after the particle has been detected, a seeming impossibility, the interference pattern can miraculously reappear when we analyze the data in a certain way. It's as if a future action reaches back in time and changes the behavior of the particle. The two-state vector formalism makes perfect sense of this. The final measurement event, the erasure, provides a boundary condition from the future that, together with the preparation from the past, forces the particle to have exhibited wave-like interference all along. The present is constrained by both its history and its destiny. We can visualize this with a simple diagram of a time-symmetric process. Picture a horizontal line representing the flow of time from left to right. At a point on the left, label it preparation. This is where the experiment begins, setting the initial state. At a point on the right, label it measurement. This is where the experiment concludes, the final observation. Now, instead of a single arrow moving from preparation to measurement, draw two arrows. One arrow points forward from the preparation event, representing the forward evolving wave function. A second arrow points backward from the measurement event, representing the backward evolving wave function. Where these two arrows meet, somewhere in the middle, is the present moment. The state of the system at that present moment is determined by the interaction of these two waves. This beautiful symmetry treats past and future not as a chain of cause and effect, but as equal partners in defining the now. The implications of this hidden time symmetry are profound. It suggests that the apparent randomness of quantum outcomes is not a fundamental property of nature, but a consequence of our ignorance. We only set up the initial conditions and then look at the final result. We are missing the full picture, which includes the boundary condition from the future. If we knew both the complete past and the complete future, the quantum world would appear perfectly deterministic. This challenges the very core of standard quantum mechanics, not by replacing its equations, but by completing them, restoring a symmetry that was there all along but hidden from our one-way view of time. It paints a vision of a universe that is not unfolding randomly, but is a consistent whole, where every moment is a unique and delicate negotiation between the echoes of the past and the potential of the future. But if the universe is a consistent whole, as the two-state vector formalism suggests, then information, the distinct arrangement of particles that defines everything from a planet to a thought, must be forever preserved. This principle of information conservation, a cornerstone of quantum mechanics, is thrown into a terrifying crisis by the most destructive objects in the cosmos. This brings us to the notorious black hole information paradox, a puzzle that has haunted theoretical physics for decades and whose potential resolution points to one of the most subtle and beautiful hidden symmetries of all. The problem was crystallized by Stephen Hawking's stunning discovery that black holes are not truly black. They slowly radiate energy and evaporate over astronomical timescales. This Hawking radiation, he argued, is entirely thermal, it's random noise, like the heat radiating from a stove, carrying no information about what fell into the black hole. Imagine writing a detailed encyclopedia of human knowledge and then hurling it into a fire. The heat and light from the fire would be the same whether you burned the encyclopedia or a random stack of phone books. The information is lost, converted into a featureless glow. Hawking's calculation suggested black holes do the same thing on a cosmic scale. They could consume a star, a spaceship, or a billion unique libraries, and all that would ever come back out is an identical, random hiss of particles. When the black hole finally evaporates completely, all that specific information about what it consumed is seemingly erased from the universe forever. This violates the sacred principle of quantum unitarity, which states that information can never be destroyed, only transformed. It's a paradox that pits general relativity against quantum mechanics in a fight to the death. The potential solution to this nightmare might lie in the most delicate and imperceptible of structures adorning a black hole's event horizon, what physicists call soft hair. This isn't hair in any literal sense, of course. It's a poetic term for an infinite set of incredibly subtle, zero-energy excitations that can imprint themselves on the boundary of a black hole. The concept builds on a profound connection between gravity and a deep symmetry known as BMS symmetry, named for its discoverers Bondi, van der Berg, Metzner, and Sachs. They found that at the far boundaries of spacetime, the null infinity where light rays go out forever, the symmetries of general relativity are much richer than anyone had imagined. Beyond the standard rotations and boosts, there exists an infinite dimensional group of transformations called supertranslations and superrotations. These are incredibly gentle, long wavelength distortions of spacetime that require virtually no energy to create. The soft hair proposal, advanced by physicists like Stephen Hawking, Malcolm Perry, and Andrew Strominger, suggests that when something falls into a black hole, it doesn't just change the black hole's mass, charge, or spin, the three properties classically allowed by the no-hair theorems. It also subtly changes the pattern of these supertranslation and superrotation charges on the horizon. It's like dropping a stone into a perfectly still pond. The stone itself is gone, but the surface of the pond is now covered in intricate, expanding ripples that encode information about the stone's size, shape, and the point of impact. In a similar way, the infalling matter imprints an incredibly faint pattern of soft hair, a specific arrangement of these zero-energy excitations, onto the event horizon itself. This pattern is a kind of cosmic braille, a permanent record of what fell in. The magic is in the evaporation. Hawking radiation is not created in the empty void just outside the horizon. It is intimately connected to the quantum fluctuations at the horizon. The proposal is that as pairs of virtual particles pop into existence near the edge, one falling in and the other radiating away, the radiated particle is subtly correlated with the soft hair on the horizon. The information about what fell in isn't trapped inside, lost forever. Instead, it is slowly and meticulously encoded into the outgoing radiation via its interaction with this intricate holographic hairstyle. By the time the black hole has completely evaporated, all the information has been transferred, like a perfect quantum teleportation from the horizon to the radiation. The random hiss is not random at all. It is an incredibly complex and ordered message, a story written in the language of particles, telling the tale of everything the black hole ever consumed. Unitarity is saved, and the fundamental laws of quantum mechanics remain intact. This incredible idea transforms our view of a black hole from a simple, destructive pit into the most efficient and secure information processing system in the universe. The event horizon is not a wall but a dynamic, quantum-critical surface, a processor that scrambles and encodes information with maximum efficiency. The hidden symmetry that makes this possible is the infinite-dimensional BMS symmetry, a vast and previously overlooked set of transformations that act as the guardians of information. They provide an infinite number of conserved charges, the soft hair, that can store an infinite amount of information, ensuring that not a single quantum bit is ever truly lost. This resolution doesn't just tidy up a theoretical loose end. It profoundly connects the physics of the very large to the very small, suggesting that the principles of quantum information and the symmetries of spacetime are fundamentally and beautifully one and the same. But if the universe truly has a smallest possible scale, a fundamental graininess to reality as suggested by loop quantum gravity, then what is the actual structure of that granularity? How can we build a theory of spacetime that is fundamentally discrete from the ground up, without ever assuming the smooth, continuous background of Einstein's relativity? This brings us to one of the most radical and geometrically pure approaches to quantum gravity, the causal set theory. Imagine the entire history of the universe, every event that has ever happened or ever will happen, not as a smooth, flowing river of time, but as a vast, shimmering cloud of individual, discrete points. Now imagine that the only fundamental relation between these points is a simple, binary question. Did one event come before another? This is the essence of a causal set. It is a collection of discrete events akin to the individual frames of a movie, with a strict partial order that defines which events can influence which others. The two fundamental axioms of this approach are breathtaking in their simplicity. First, spacetime is discrete. There are a finite number of fundamental atoms of spacetime within any finite volume. This solves the problem of the singularities that plague general relativity. There are no points of infinite density because you simply cannot pack an infinite number of spacetime atoms into a finite space. The universe has a finite information density. Second, all that truly matters is the causal relationship between these atoms. The entire, rich geometry of spacetime, its curvature, its topology, even its dimensionality, is not a primary concept. It is a secondary, emergent property that arises from the intricate web of who caused whom. In this view, the smooth, four-dimensional continuum we experience is a kind of large-scale illusion, an approximate averaging of a much deeper, discrete causal structure. It's like looking at a pointillist painting from a distance. The individual dots vanish and a smooth image emerges, but the true foundation is a collection of distinct points. Visualizing a causal set is a challenge for our continuum-loving brains, but we can use a powerful diagrammatic tool, the Hasse diagram. Picture a scatter plot where each point represents a fundamental event in the history of the universe. Now draw a line from one event upward to another event only if the first directly caused the second, with no intermediate event in between. This creates a vast, branching, web-like structure that flows upward from the past to the future. The entire structure is a web of causality, a cosmic family tree for every event in reality. The hidden symmetries in this framework are the symmetries of this web, the transformations you can make to it that preserve all the causal relationships. If you can shuffle the events around without changing which events precede which others, you have discovered a symmetry of the causal set. These symmetries are fundamentally different from the continuous symmetries of traditional field theories. They are the symmetries of order and information. The most dynamic aspect of this theory is how this universe grows. The causal set is not a static block. It is conceived as being in a constant process of ongoing creation, with new events spontaneously coming into existence. This process is often modeled as a random, sequential growth. Imagine building the causal set one event at a time. A new event emerges from the quantum foam and must choose its past. It does not create new links to every event in the past. Instead, it only links to a subset of them its immediate causal parents. The precise rules of this growth, the probabilities that a new event will choose a specific set of parents, are the dynamical laws of the universe in this theory. Different growth laws would produce causal sets that, when averaged over, give rise to different emergent continuum geometries, perhaps one that is flat and four-dimensional like ours, or one that is wildly curved and has 11 dimensions. The challenge for physicists is to find the unique growth law that inevitably produces a large-scale structure that looks like our universe. This approach offers a stunningly elegant solution to the mystery of the arrow of time. In the block universe view of general relativity, past, present, and future all equally exist, and the flow of time is an illusion. But in causal set theory, the now has a real meaning. It is the ever-advancing frontier where new events are being born. The universe is literally growing, and the direction of that growth defines the arrow of time. The reason we remember the past and not the future is because the past is fixed, its events exist and their causal relations are set, while the future is truly open, not yet created. This presents a picture of a universe that is not just evolving within time, but one whose very substance is time itself, a perpetual process of becoming that weaves the fabric of space-time one causal connection at a time. And so we arrive at the ultimate quest, the dream that has guided physics for over a century, the search for a final theory, a single, all-encompassing framework from which every law of nature, every particle, and every force emerges as an inevitable consequence. This isn't just about finding more equations, it's about discovering the universe's foundational bedrock, a maximally symmetric structure so profound and elegant that it admits no further simplification. Imagine a unique mathematical object, perhaps an exceptional Lie group like E8 or a deeper, yet undiscovered principle, whose inherent properties and symmetries automatically generate the reality we experience. In this vision, the frantic quantum dance of particles, the graceful curvature of space-time, and the very existence of matter and light would all be seen as different melodies played on a single, fundamental instrument. The challenges on this path are as immense as the ambition itself. First, there is the problem of uniqueness. How do we know there is only one such ultimate theory? The mathematics we use to describe the world is a human invention, and it's filled with an abundance of beautiful, complex structures. Selecting the right one from this infinite menagerie seems almost arbitrary without a guiding principle. Then there is the problem of emergence. Even if we found this perfect mathematical jewel, how do we get from its pristine, abstract symmetries to the messy, complex, and apparently broken symmetries of our everyday world? Why would a theory of perfect balance produce a universe that is so manifestly unbalanced, with an overwhelming preference for matter over antimatter and a specific set of forces with their particular strengths? This journey from the absolute to the apparent requires a mechanism, a cosmic story of symmetry breaking that turns a potentiality of everything into the actuality of our specific something. This search forces us to confront deep philosophical questions about the nature of reality itself. Is the universe ultimately mathematical? Are we discovering these laws or, in some sense, inventing them? If the final theory is based on a unique mathematical structure, it suggests a form of Pythagoreanism, the idea that reality is at its heart mathematical. This raises the possibility that all logically consistent universes might somehow exist, and we simply find ourselves in one that is compatible with conscious life. The anthropic principle and the multiverse idea become not just convenient excuses for fine-tuning, but potentially necessary components of a complete cosmological picture. The ultimate symmetry might not describe a single universe, but the entire landscape of possible universes, with ours being just one particular expression. Now let's weave together the themes from our journey. This final theory would be the grand unification of every hidden symmetry we've explored. It would incorporate the particle-partner symmetry of supersymmetry to tame the quantum wildness. It would provide the geometric foundation for the extra dimensions of string theory, explaining why the specific Calabi-Yau shape of our universe was selected, perhaps through a process of cosmological natural selection. It would reveal the holographic principle and the add-s/CFT correspondence not as clever tricks, but as fundamental aspects of how information and gravity are two sides of the same coin. The conformal invariants we see in critical phenomena and Penrose's cyclic cosmology would be low-energy echoes of this maximal symmetry. It would explain the bizarre non-locality of quantum mechanics and the perfect preservation of information, not as paradoxes, but as necessary features of a universe built from a causal set or a non-commutative geometry where spacetime itself is emergent. The ultimate symmetry would be the source from which all other symmetries flow. It would dictate why CPT symmetry is unbreakable, serving as the bedrock of causality and quantum field theory. It would explain the origin of the gauge symmetries that give rise to the electromagnetic weak and strong forces, showing them to be inevitable fragments of a larger whole symmetry that was present at the universe's birth. The mysterious properties of dark matter and neutrinos would find their place as inevitable consequences of this structure, their hidden sectors and tiny masses arising naturally from the mathematics. Even time itself, with its apparent arrow, would be seen as an emergent property of the growth of this fundamental structure, a necessary outcome of its dynamic evolution from a state of perfect symmetry to our complex, asymmetric present. This grand vision is more than a scientific goal. It is a testament to humanity's enduring belief that the cosmos is fundamentally comprehensible, that beneath the overwhelming complexity and apparent chaos lies an order of breathtaking beauty and simplicity. The journey to find it has already revolutionized mathematics, reshaped our understanding of space and time, and revealed a universe far stranger and more interconnected than we ever imagined. Whether or we ever hold the final equation in our hands, the pursuit itself has given us a deeper, richer, and more wonderful view of the cosmos we call home. The search for ultimate symmetry is ultimately a search for meaning written in the language of mathematics, a quest to understand not just how the universe works, but why it exists at all. From the elegant dance of supersymmetric particles to the mind-bending holographic projection of our reality, these 30 theories each illuminate a different facet of a cosmos built on profound and hidden symmetries. We've journeyed through the intricate, multi-dimensional shapes of string theory's Calabi-Yau manifolds and seen how their mirror pairs might describe the same physical universe. We've grappled with the cosmic censorship that veils the universe's singularities and explored how the perfect, unbreakable rule of CPT symmetry underpins all of reality. We've considered the possibility that spacetime itself is not fundamental but emerges from a vast network of quantum information, or the intricate braiding of enyons in a topological quantum computer. Each idea, from the radical timelessness of the two-state vector formalism to the granular, growing universe of causal set theory, represents a different path in our quest to understand the deepest order of existence. What unites them all is a breathtaking pursuit of unity, a drive to see the cosmos not as a collection of disparate phenomena, but as a single, elegant mathematical structure expressing itself in countless ways. Whether through the scale-invariant patterns of a conformal field theory at a critical point or the audacious cosmic cycles of Penrose's conformal cyclic cosmology, we find a recurring theme. The universe seems to operate on principles of balance and connection that are far more sophisticated and beautiful than our everyday experience suggests. This isn't just abstract philosophizing. It's a rigorous scientific endeavor to decode the very source code of reality, to understand why the constants are fine-tuned for life, and to discover if the forces we know are merely fragments of a grander, more symmetrical whole that existed at the moment of creation. The beauty of this quest lies as much in the mystery as in the discovery. For every answer we think we have, like the Higgs mechanism giving particles mass, a deeper question emerges, like the naturalness problem that points toward physics beyond our current models. The fact that we can even conceive of these ideas, from the exceptional simplicity of the E8 group to the wormhole connections of ER equals EPR, is a testament to human curiosity and our innate desire to find pattern and meaning in the cosmos. It reveals a universe that is not just stranger than we imagine, but stranger than we can imagine, yet still partially comprehensible through the language of mathematics and the power of rational inquiry. This journey through cosmic symmetry doesn't end here. It's an ongoing conversation, a collective effort of countless minds striving to see the universe more clearly. We want to hear which of these theories resonated most deeply with you. Was it the holographic principle that reshaped your concept of reality, or the profound implications of quantum Darwinism explaining our shared experience? Share your favorite in the comments below and let's continue the discussion. If your curiosity is ignited and you're eager to dive deeper into any of these concepts, we've included links in the description to further reading and videos that explore topics like string theory, loop quantum gravity, and the black hole information paradox in greater detail. The search for understanding is one of our most human endeavors, and every new perspective brings us a little closer to glimpsing the true, magnificent symmetry hidden within the heart.